Hello everyone, welcome to Scalar, and in this particular video we're going to look into dynamic programming. And before we move on with this particular session, please make sure to subscribe to our channel so that you don't miss our upcoming videos, and also leave a like if you enjoy our content. If you have any queries, leave a comment down below and we will be addressing your concerns. So now let's look at what exactly will be covered in this particular video. So first of all, we start off with the introduction to dynamic programming. After the introduction, we'll be solving certain problems using dynamic programming. Number one, we'll be solving coin change problem. After that, we'll be looking into longest common subsequence. Then we'll look into edit distance using dynamic programming. Then we'll be looking into the knapsack problem, and finally we'll be looking into minimum cost path sum. So these are the things which will be covered in this video. Now let's begin.
My name is Tarun Malhotra. I am a lead software engineer here at InterviewBit and also take classes at Scalar Academy. Today's session is going to be a session which deals with basics of dynamic programming. That is, what is this paradigm? What kinds of questions can you solve using this paradigm? And we would try to solve some simple problems on DP today. But going forward, as and when we move on with these sessions, you should be able to be more and more confident with the idea of DP and how to apply dynamic programming in the problems where you can actually model those problems as DP problems. Okay, cool. So before actually coming to the definition of dynamic programming, describing what this paradigm is, let's take an example with whose help we'll actually figure out that what is the reason of coming up with a paradigm like this. Okay, what kinds of problem can you actually hope to optimize further using this paradigm of dynamic programming? Cool. Yeah, the very first problem that we'd want to see without actually knowing about DP would be the problem of Fibonacci numbers. I am sure that most of you would have heard about this problem of Fibonacci numbers. The problem is as follows. You want to figure out the nth Fibonacci number, and the Fibonacci numbers are as follows. The first Fibonacci number by definition would be equal to, let's say, 1. The second Fibonacci number would be equal to, let's say, 1 again. And now for any Fibonacci number n, where n is greater than 2, the number can be defined using the previously defined Fibonacci numbers. Okay, so for fn, where n is greater than 2, you can say that the nth Fibonacci number would be equal to the summation of n minus 1th Fibonacci number plus the n minus 2th Fibonacci number. I hope this definition should be clear to everybody. The first Fibonacci number is 1, the second Fibonacci number is 1. Now, and for any n which is greater than 2, the nth Fibonacci number would be the summation of the last two Fibonacci numbers. Okay, the n minus 1th and the n minus 2th. Now, I am pretty sure that just by looking at the definition of Fibonacci numbers, everyone would be clear that the definition of Fibonacci numbers is nothing but a recursive definition, right? You are actually defining a number recursively using the previously defined numbers. Okay, so how would you go about solving this? The problems of recursion can actually be very easily visualized by drawing a recursive tree. I hope all of you should be able to appreciate that. Let's take an example and see if we are able to appreciate that completely. Okay, so let's say I wanted to compute the 7th Fibonacci number. Okay, I wanted to compute the 7th Fibonacci number. So let's say, yes, this is a state that I want to compute the 7th Fibonacci number. Now, by definition, if I want to compute the 7th Fibonacci number, I should go to the number n minus 1th and the number n minus 2th. Okay, so f7 would actually be nothing but a summation of f6 and f5. I hope this should be crystal clear to everybody that this is just a recursive definition. Now, we do not know what f6 is, and f6 can again be computed using the same definition that we have given above, by saying that f6 would be nothing but f5 plus f4. You can keep on drawing this tree, and now f5 can be represented by, let's say, f4, f3. f4 can be represented as the summation of f3 and f2, where f3 can be represented as the summation of f2 and f1. Now we know that we need not define this f2 into smaller subproblems, because by definition I already know that f2 is equal to 1 and I already know that f1 is equal to 1. So now I know that the answer to this is already known, so no need to divide it further. The answer to this is already known, no need to divide this further. The answer to this is already known, no need to divide it further. So we call these cases, which are trivially easy to answer themselves in any recursive problem, as the base case of a recursive problem. Okay, so also just to give a context why we are discussing about recursion should be very clear in a bit when we actually move from recursion to DP. So just hold on for a while and understand this properly. Okay, so this would be a base case, this would be a base case, that is a problem for whom we know the solution already. This would also be a base case. Now, is F3 a base case? No, F3 is not a base case because I do not know the answer of F3 already. So I would define F3 into smaller problems as the summation of F2 and F1. Now, F2 is a base case and F1 is a base case. Now, let's come to the node which is still remaining, F4. You would realize that this F4 would again be expanded as an entire subtree. Does it make sense? F4 would be expanded to the summation of F3 and F2, so on and so forth. F3 would be expanded to a subtree. F2 would be again expanded to a subtree, and this would go on. And you can also look at F5. This would also be expanded to a subtree where the base cases would only be F2s and F1s. I hope this makes crystal sense to everybody. So we represented this Fibonacci problem as a recursive tree because it's a recursive problem. Now, once I have defined this, now to compute this problem, you will essentially have to compute every single node in this recursive tree, right? You can start from the very top and then you will be computing every single node in this recursive tree. Now the problem arises that how much time would I actually require to compute the value of F7 or any F9? To compute the value of F7, I will have to compute this entire tree. So to figure out, estimate the time required to compute that, I would suggest that let's first of all estimate the number of states that are there. Okay. From looking at this diagram and realizing it intuitively, you would realize that first of all, what is the depth of this tree, right? So you start with F7 and what is the farthest distance where you would be actually finding a base case? The farthest distance would actually be 7 in this case because you started with F7. And in each iteration, at each level, you at least have one node which was just reduced by 1. Okay, so the depth of this tree is 7 in this case, or to speak generally, the depth of this tree would be n if you are computing the nth Fibonacci number. Okay, if the depth of the tree is n, the fan factor of the tree is 2, you would realize intuitively that the number of states here would be of the order 2 power n. I hope this makes sense to everybody. The number of states would be of the order 2 power n. Now, let's actually figure out the amount of time required to compute a state. That I would claim time required per state in this case is nothing but a constant amount of time. Let's call it order 1. Why? Because if I want to compute this state and I already know the answers to F4 and F5, I just need to add them up. So the time required per state, if you are already assuming that you know the states below it, would be order 1. There are 2 power n states to be computed. Every state would be computed in order 1 time. So time complexity is definitely going to be exponential. It's definitely going to be 2 power n. This is one way to look at it. The other way to look at it would be solving the recurrence relationship. The recurrence for this problem would be that you have a problem of size n. You are reducing that problem of size n to a problem of size n minus 1 and a problem of size n minus 2, and you are combining them by spending some constant amount of time. If you solve this recurrence, you will again get the same time complexity, which is exponential time complexity 2 power n. I hope till this point in time, everything makes sense, that to solve a Fibonacci number, you are essentially giving exponential time. Now let's actually draw some observations in the tree that we have just formulated. The observation that I want you guys to draw, that there are a lot of states that you are computing that you could have avoided computing. Okay, listen it again. I am saying that there are a lot of states here which could have been avoided. You could have avoided computing them just because you already knew the answer of those states. Okay, let's see some examples. So have a look at it. You have already computed f of 3 here. Does it make sense? But you are again seeing this f of 3 here. And that's not a... When you actually solve this f of 4, you again solve f of 3 here, right? And when you actually solve f of 5, you are essentially going to solve f of 4 and f of 3. This f of 3 is again repeated. To solve this f of 4, you are again going to call f of 3, which is again repeated. So you see that there is a lot of repetition happening here in the states that we have defined. Okay, in this recursive tree, there are a lot of repetitions, and you could have actually avoided doing those repetitive computations. Try to understand it's not only about one state being repeated, it's about so many entire subtrees being repeated. Okay, so if this F3 was already known, you could have avoided computing this entire subtree. Now, if this F4 was already known, you could have avoided computing this entire subtree. If this F5 was already known, you could have avoided computing this entire subtree. And this, if F2 was already known, which is a base case, you could have avoided computing this subtree. And this F1 is again a base case. You can just remove it because that's a problem that you already know, or you can assume that F2 could have been divided into F1 and something. And this is, so basically this is just a base case. So now you actually see that the problem, which was a binary tree in the beginning, is now reduced to nothing but a linked list. Does it make sense? There is no tree here now. The recursive tree is no longer a tree in this case, just happens to be a list of some states that you are computing. Okay, so you see that the number of unique states that you have, is just of order n. You only have order n unique states here, but in the recursive tree you had 2 power n states, and now you actually get the idea that you could have actually stored the values of these states, and whenever you wanted to get those values again, rather than recomputing them, you could have just utilized the answers that you already had. I hope this makes sense to everybody. So we have actually reduced the problem which had so many number of states into a problem with lesser number of states, just because the number of unique states that I had, was smaller than the number of total states that I was seeing. Okay, so this is the basic idea. Now let's actually come to the definition of dynamic programming and see how this idea can be extended and can be utilized to solve a lot of problems. Okay, cool. So let me actually take you to one interesting definition of dynamic programming. A way to put it would be that dynamic programming is a method of solving complex problems by breaking the problem down into collection of simpler subproblems. So you have a bigger problem. You are breaking that bigger problem into a collection of smaller problems of the same type. Now you end up solving those smaller problems exactly once, and then you utilize those solutions to construct the answer to a bigger problem. Okay, so what exactly you are doing? Let's look at this problem. That you have a problem which could have been solved using smaller subproblems. So Fn could have been solved using the answers to smaller subproblems, where n would be less than this n dashed. And now you end up solving those subproblems exactly once. So you are only going to solve F6 exactly once, F5 exactly once, F4 exactly once, and so on and so forth. And you are then going to utilize the answers to those smaller problems to construct the answer to a bigger problem. Okay, so this is exactly what we will end up doing here. Let me actually just tell you how we can solve this problem here, right? So you know this is a recursive problem. So a simple recursive code of this solution would be that, let's say you wanted to solve, let's say you want to return an int. You want to say int get Fibonacci number. It takes as input the nth Fibonacci number that you want to return. So this is a recursive code. In any recursive code, you start with the base case. This is something that you should always remember. So you start with the base case. The base case here happens to be n equal to 1 or n equal to 2, right? So what do? You say, first of all, let's check for a safety case that if n is less than 1, then let's say it's not defined, so you return -1, let's assume. Now, if this is not the case, if n happens to be less than or equal to 2, that is if n happens to be exactly 1 or 2, that is you want the first Fibonacci number or the second Fibonacci number, you are just going to return 1. This is the base case that we have by definition. Now, after this, for any other n, you would simply be calling f of n minus 1 and f of n minus 2. So a simple recursive solution would look something like this. That's simply going to return get fib for n minus 1 plus get fib for n minus 2. This is a simple recursive problem, but you see a lot of recomputations are happening here. So what do? You just add memoization. So what do? This is plain recursion. In plain recursion, you just add something which is called as, let's say, memoization. Just because you see a lot of states being recomputed again and again. So rather than recomputing them, let's actually store them and only compute them exactly once. So how to store them? Let's say you now have an array of size, let's say n, which is initialized by, let's say, -1 to begin with. Make it n plus 1 if you are using it. Let's assume this was one indexing array. Okay. Now you initialize the base cases here by, or let's say, yeah, you can initialize the base case here by saying that f of 1 would be equal to f of 2 would be equal to 1. And now what do? When you actually want to compute that, you first check if that n minus 1th value was already computed or not. So rather than just doing this, you actually do something else. So now you first check if f of n minus 1 was still equal to -1, that is, it was still not computed, only then you make a call to compute it. So you now say f of n minus 1 would be equal to get fib n minus 1. You now have the value here. Similarly, you do that for f of n minus 2 and see if that is equal to -1. You compute the value and store it there. And then once you have done both of these operations, you simply return the summation of them. So just by changing the solution a bit, you have reduced a lot of time complexity. The time complexity now becomes order n. Okay. The space complexity also becomes order n. Cool. So this was a very, very basic problem. Let's move ahead. You can actually reduce the space complexity, but let's leave it as a homework for you guys to understand that how you can actually reduce the space complexity here. So now let's actually move to a lot more interesting problems on dynamic programming. And before that, let me give you the formal definition here, which will help us to figure out when to use dynamic programming. Okay. So the formal definition of dynamic programming is that a problem which can be modeled, into dynamic programming if it has two features. So what are the features for a problem to be modeled in dynamic programming? The first feature is that the problem exhibits optimal substructure. What is optimal substructure? We'll just come to it in a moment. The second feature is that you should be seeing overlapping subproblems. So these are the two features that you look in any problem to make sure whether that problem can be solved using the dynamic programming paradigm or not. Now let's explain these two features in more detail. Okay. Optimal substructure feature simply means that your problem, the solution to the problem, the optimal solution to a bigger problem can actually be constructed using optimal solutions to smaller problems. Okay. So the optimal solution to a bigger problem can be computed using the optimal solutions to smaller problems. So this is the optimal substructure property. That is, let's say here you want to compute f of 7. Can you actually compute f of 7 using the smaller problems ka answers? Can you compute it using f of 6 and f of 5? Yes, you can do that. Right? Can you compute f of 6 using f of 4 and f of 5? Yes, you can do that. So a problem which shows that you can compute an answer to a bigger problem using the solutions to smaller problems is called as optimal substructure. The problem being showing optimal substructure. Okay. The second part is that you should see a lot of overlapping subproblems. Okay. So what is overlapping subproblems? That is, you should be able to see subproblems which were otherwise being repeated several times, and now you can just memorize them so that you do not compute the same problem again and again. Okay, so just because a problem which exhibits overlapping subproblems, you see an opening that yes, you can exploit that overlapping subproblems and reduce substantially the number of subproblems that you actually compute. Okay, so overlapping subproblems, that is, you should see a subproblem being computed again and again. The moment you see that, you can stop doing that, and then you call your solution to be a dynamic programming solution. Okay, so you see subproblems being computed multiple number of times. Now, these are the two features which will help you to judge whether a problem can be solved using a dynamic programming paradigm or not. Now, keeping this in mind, let's try to solve a few problems, and then we would keep on building on the concepts using those problems. Okay. The very first problem that I would want to discuss with you guys is called as the problem of stairs. So this is a problem that is actually asked in several product companies. This problem was asked at Morgan Stanley. This problem was solved at Amazon, was asked at interviews of Amazon. This problem was also asked at interviews of Intel. So this is a problem which you, just by looking at the companies that have asked this problem, you guys would have gotten an idea that yes, this happens to be a very, very interesting application of dynamic programming. Okay, cool. Let's define the problem. The problem is as follows, that you have n stairs. Okay, you have n stairs. So let's call it the first stair, the second stair, the third stair, and let's call it the nth stair. You have n stairs. Let's assume originally you are at the first stair. Okay, so originally you are at the first stair. Okay, now at every stair you have two options. Option one that you have is to just from the ith stair go to the I plus 1th stair. The second option that you have is that from the ith stair you go to the I plus the second stair, so I plus 2th stair. Okay, so what does that mean? So let's say you were at the first stair. The first option that you have is to go to the second stair, or you could have actually chosen to directly jump to the third stair. You could have avoided going to the second stair and directly jump to the third stair. These are the two options that you have. The question asks you that you want to figure out the number of ways to reach the nth stair from the first stair. What does that mean? That how many distinct number of ways are there in this problem which will take you from the first stair to the nth stair. I hope the problem is clear to everybody. Okay, cool. Now let's actually look at a couple of examples and see what kind of a pattern do we observe. Okay, let's take an example for what happens if the number of stairs was only equal to 1. So let's say there is only one stair. You are at the first stair, you only have to reach the first stair. How many number of ways that are there? The number of ways that you have is only one. That you can choose not to do anything because you are at the first stair itself. You cannot do anything else but to stay at that stair. Now let's look at the example 2. What happens if you have n equal to 2? That you happen to be at the first stair and you have to reach at the second stair. How many distinct ways do you have? So you have at the first stair, you have two options, either to go to the second stair or the third stair. The third stair does not exist. So there is only one option, that you can just go to the second stair. And the moment you go to the second stair, you have reached the solution that you have. You can only stay there, cannot go anywhere else. So the number of ways for this n equal to 2 problem would also be equal to 1. Now let's look at the example 3 that we have. So let's say now we have n equal to 3. You are at the first stair, you want to reach at the third stair. What all options do you have, people? You are at the first stair, you have two options. Either from the first stair, you can go to the second stair, or you have the second option which says from the first stair, you can go directly to the third stair. Okay? If you actually choose to do the second option, that is from the first to the third, you have already reached your destination and you can only stay there. You cannot do anything else. Now let's look at the first case that you assume, that you can move from the first to the second. If you move from the first to the second, what options do you have from the second stair onwards? You can either go to the third stair or you can jump to the fourth stair, but fourth stair does not exist. So you only have one option, that is to go to the third stair. Now this also completes the entire path and you have reached the solution. So you see that there are two ways to solve this problem. If n was equal to 3, the number of ways that you have is 2. Does it make sense to everybody? We have seen 3 examples here. N equal to 1, n equal to 2, and n equal to 3. And we now know that what are the number of ways that you have to reach to your nth stair. Cool. We have understood the problem. Now let's see, can we, so how I would approach to a greedy problem. Okay? One thing that I just told you, that it's very important to check whether these features are there in the DP problem. So let's check whether these features are actually there in the DP problem. The first feature is there an optimal substructure? Okay. So do you see an optimal substructure? What does that mean? Can you solve a bigger problem using the answers to smaller problems? Okay. So let's try to answer that. Let's take any bigger problem. Let's take n equal to 5. Let's assume that you had 5 stairs. Now let's assume if you want to compute the number of ways to reach the 5th stair from the first stair, and somehow you already know the answer to number of ways to reach the 4th stair and the number of ways to reach the 3rd stair. Let's say somebody told you that number of ways to reach the 3rd stair is equal to A and the number of ways to reach the 4th stair is equal to B. Now, can I actually compute the number of ways to reach the 5th stair? Okay, let's try to find out. So if I want to reach the 5th stair, you guys tell me what are the options that I have for the penultimate step. If the last step that I make happens to be the 5th stair, that is I want to reach the 5th stair, what options do I have for the penultimate stair? That is the second last stair that I would have taken. The option 1 that I have for the penultimate stair is that I would have been at the 4th stair. Does that make sense, guys? From the 4th stair, you could have gone to the 5th stair. This is one option. The second option that you have for the penultimate stair would be that you could have actually gone from the 3rd stair to the 5th stair. I hope it makes sense. The options that you have for the penultimate stair would either be from the 4th stair or from the 3rd stair. Okay? So you could have actually, one option is you could have come from the 4th stair to the 5th stair. The other option is that you would have come from the 3rd stair and jumped directly to the 5th stair. Now, I know the number of ways I would have reached the 4th stair from the 1st, which is nothing but B. If I know that from the 4th stair, I only have one option to go to the 5th stair, which is just to take a single step, I will multiply this by 1 because I only have one option from the 4th stair. So B into 1. Then the second option was that I come to the 3rd stair somehow and then jump directly to the 5th stair. If I come to the 3rd stair somehow, number of ways I already knew, let's assume was equal to A. So I do A. And now from 3rd to 5th, if I want to have a jump, I will just multiply it by 1. These were the two mutually exclusive and exhaustive options that I had. So I will just add them up to get my complete answer. So number of ways to reach the 5th stair from the 1st stair would be nothing but the number of ways to reach the 4th stair multiplied by 1 plus the number of ways to reach the 3rd stair multiplied by 1. Okay, you can actually generalize this and say that number of ways to reach the nth stair is nothing but number of ways to reach the n minus 1th stair multiplied by 1 plus number of ways to reach the n minus 2th stair multiplied by 1. So this also happens to be a problem which very interestingly mimics the problem that we had for Fibonacci numbers. Does that make sense to everybody? Have we actually just proven to ourselves that we see an optimal substructure here, that we can actually solve a bigger problem using smaller problems? If you can see that optimal substructure is there, using that we have arrived at a recurrence relationship as well. Now looking at this recurrence relationship, we also see that a lot of states would be repeated. So yes, there is an overlapping subproblem point here as well. So this problem can be very easily solved using dynamic programming. Does that make sense to everybody? that you have actually proven to yourself that this problem actually has overlapping subproblems and optimal substructure both. So you can solve this problem using the dynamic programming way. Cool. So once we have established that how to look at a problem and figure out whether you can solve it using DP approach or not, let me actually describe to you 2 ways to solve a DP problem. Okay. So this is one way to look at a DP problem. Hold on for a while. In the next question or so, I would be discussing another way of looking at DP problems and solving them. In the meanwhile, let me tell you that there are 2 broad ways to solve any DP problem. Okay. One of them happens to be a top-down approach. What is meant by a top-down approach? A top-down approach means that you just write a recursive code as we did in our first problem for Fibonacci, and with the recursive code, just because you see that there are overlapping subproblems, and you can actually reduce the time complexity by memoizing those subproblems. That is, storing the answers to those subproblems. You can just, in the recursive code, just throw in memoization, and you would get a solution for the top-down approach using DP. I hope it makes sense. That what did we do in our first solution? We just wrote a recursive code and just added memoization. That is, we just added an array where we actually just added some states where we actually stored the answer to those states and did not compute them again. So a simple recursive problem code with throwing in memoization in it would actually solve your problem top down. Why do we call it top down? That you actually start solving your problem from the answer that you want. That top problem gets divided into smaller problems, and this keeps on happening. So you move from the top to the down. This is one way of solving DP problems. The second approach of solving DP problems is bottom up. What does that mean? The bottom up approach means that you actually start constructing your DP solution from the base case. Okay. So you actually have the answers to base cases already. This is what we know. You already have the answers to base case. Using the answer to those base case, compute the state that you could have computed just by using those answers. So in case of Fibonacci, if I know the answers to f of 1, which is a base case, and f of 2, which is a base case, both of them were equal to 1. Using these two, can you tell me what state can I compute? Using these two, I am pretty sure that you guys would be able to appreciate that you can compute, using these two states, you can compute the third Fibonacci state, which is just a summation of f1 and f2, which happens to be 2. Now you are constructing your solution bottom up. You start with the base cases and you keep on constructing your solution. Now you have the answer to f of 1, f of 2, and f of 3. Which state can you compute using this information? So my suggestion would be that you can now use the answer to f of 2 and f of 3, and you can compute the answer of f of 4. Does that make sense? It would just be the sum of them, which would be equal to 3. Now you have constructed the answers till f of 4. Now you can construct thereafter as well. So now you can use the answer to f of 3 and f of 4 and create the answer to f of 5, which happens to be just the sum of them, which happens to be 5. So you would see that you can just keep on creating answers, constructing answers in the bottom-up approach as well. So this was the first answer that you knew just by the base case. Second answer that you knew just by the base case. The third answer that you computed was this. The fourth that you computed was this. The fifth that you computed was this. And the sixth would be just using f of 4 and f of 5, you can compute f of 6, which would just be 3 plus 5, which is 8. And this would be the sixth step that you compute. So you now understand that there are two ways to solve DP problems. You can either write your code in a top-down approach, which is recursive plus memoization, or you can write your code in a bottom-up fashion, which is just by using the base cases, you keep on building your solutions to bigger and bigger problems. Okay, so this was just a big bit of a digression that we took to explain that to you, that different ways of solving DP problems. Before that, we made sure that all of us understand that DP problems that can show the features of optimal substructure, that is a bigger problem being divided into smaller problems, and utilizing the answers to smaller problems to solve the bigger problem. This is the first feature that problems being solved using dynamic programming paradigm should have. The second feature that we have is of overlapping subproblems. That is, when you divide a bigger problem into smaller problems, you see a lot of smaller problems being overlapping. And you can optimize them by having memoization, that is storing the value somewhere, and the next time you see the same problem, just utilizing the value and not computing it again. So these are the two features that any problem should show if you have to solve that problem using dynamic programming. Cool. Now let's move ahead, and then using the next question, I would try to explain to you guys that what is the difference between greedy solutions versus dynamic programming solutions. So we would look at a problem and see in what problems do you see greedy solutions not being able to solve the problem for you and you choosing to go to a DP solution. Okay, cool. The problem is a problem which is again a very famous problem, problem of robbers. So this is the problem of robbers. This problem, again, we have seen this being asked in the interviews of Amazon, and we have asked this problem being asked in the interviews of the shop. Okay, so these are the two companies that we have seen this problem being asked at. Now the problem is as follows. You are a robber. Unfortunately, you are a robber. Okay, you see a street where there are n houses. You see a street where there are n houses. Every house has some gold coins in it. Okay, so let's assume the first house has 2 gold coins, second house has 7 gold coins, third house has 9 gold coin, 3 and 1. So these are the gold coins that are present in these houses that you see on a single street. Okay, now you are a robber. So what would you do? You would want to rob these houses. Okay, what is the function that you would want to maximize? You would want to maximize your robbery. Does that make sense? So if unfortunately you happen to be a robber, what would be your optimization function? That you would want to maximize your robbery. Okay, if you want to maximize your robbery and there was no constraint, then you would have actually robbed every single house. Does that make sense? Right? But let's now add, to make the problem interesting, let's add a constraint. The constraint is as follows, that every 2 adjacent house on the street are connected by an alarm. Okay, so you see an alarm between the first and the second house. You see an alarm between the second and the third house, between the third and the fourth house, the fourth and the fifth house. So you see there are some alarms being placed between every 2 adjacent house. What does that alarm do? That alarm simply rings if any one of these 2 houses are being robbed. So what does that mean? It means that if this house is being robbed by you, this alarm would go up and this alarm would also go up. So if this alarm goes up, the people in this house will wake up and you will no longer be able to rob this house. Similarly, if this alarm goes up, people in this house will also wake up, and unfortunately or fortunately for them and unfortunately for you, you cannot rob this house also. Okay, so this is the problem, that the moment you rob one house, there are your left house and the right house now cannot be robbed. I hope everybody gets the problem. Okay, how would we go about solving it? The answer to that, so let me just remove the things that I just drew over this problem, and let's first of all see, can I actually come up with a greedy solution to this problem? So before actually answering can I have a greedy solution, let me actually define for you very quickly what a greedy solution is. A greedy solution is that without looking at what holds for you in the future, without looking at the future numbers, can you just make a call by looking at the number that you are just seeing? By looking at the thing that you are just seeing, can you actually figure out the solution to the entire, can you actually make a choice by looking at the current number? So what does that mean? You can claim that you have a greedy solution if you can think in this way, that just by looking at this house, the first house, can you make a decision of robbing this house or not robbing this house? Just by looking at the first house, can you make a decision of robbing this house or not robbing this house? Is it possible? You cannot. Similarly, can you say, I will never rob the first house? You cannot do that. You will actually have to look at the houses thereafter to figure out whether robbing this house makes sense or not. Right? Why do I say so? Because the moment I rob this house, I am changing the landscape of the problem. The moment I rob this house, I am enforcing a constraint on me that I can no longer rob this house. Does that make sense? And without looking at what holds for me in the future, would I ever be fine with imposing these constraints? No. So that is why I would tell you that greedy solution here would not work. Just by looking at this 2, you cannot make a decision whether to rob it or not. Similarly, just by looking at this 7, you cannot make a decision whether to rob it or not. So the problems where you have a choice, the problems where you have a choice and you cannot take any choice greedily without looking at what holds for you in the future, greedy solutions won't work. So here, greedy solutions won't work. That may make us a bit unhappy that why greedy solutions are not working here. Okay, so let me just define the problem again. Whenever you see a choice or a set of choices, you see a set of choices and you cannot make a greedy decision, greedy problems won't work. Okay, so now if greedy solutions won't work, let's actually try if we can see that a dynamic programming solution can work. What does a dynamic programming solution do? It essentially allows you to explore all the possible choices that you had. So what does a DP solution do? The moment you see a set of choices and you see that you cannot make a choice randomly, you cannot just greedily make a choice, DP solution would say that let's explore all the choices that you have. DP solutions would allow you to do that you can actually explore all the choices that you have. And if you can explore all the choices that you have, then you can think in DP direction. Greedy won't work. Let's think the dynamic programming way. Before actually making sure that, before actually jumping to dynamic programming, let's see if the 2 features that we discussed before, does those features hold for this problem or not. The first feature that I told you was, does this problem show optimal substructure? What does that mean? If you know the solution to a smaller problem, can you know the solution to a bigger problem? Okay, so let me prove to you guys that yes, this problem does have optimal substructure. Okay, so let's actually come to the first feature that we had of optimal substructure. Let's actually prove to ourselves that yes, optimal substructure as a property is being held in this example. Okay, how to prove that? Let me give you an example. So let's say somebody told you that, hey man, don't worry, I know the best answer for robbing houses till this point, till the first 4 houses, and I'm telling you that I definitely robbed the last house. Okay, so I'm telling you the best answer, the best number of gold coins that I can accumulate by robbing the first 4 houses and making sure that I rob the 4th house would be something like this. Okay, somebody told you this answer. Let's call it maximum robbery for the first 4 houses. Somebody also told you the answer to another question, that I am robbing the first 3 houses, man, and I have definitely robbed the 3rd house. I also know the answer to that. So somebody tells you that yes, maximum robbery 3 ka answer you already know. Now if you know the answer of maximum robbery 3 and maximum robbery 4, can you actually construct the answer of maximum robbery 5? Yes, you can do that. Why you can do that? Because for the 5th house, you have 2 choices. Either you can rob this house or not rob this house, right? If you choose to rob this house, what is the constraint that you are imposing on yourself? The constraint that you are imposing on yourself is that you can no longer rob the 4th house. Does that make sense, people? If you're robbing the 5th house, the constraint that you're making on yourself is that you cannot rob the 4th house. So what is the house that you can rob now? You can rob the 3rd house for sure. So if you want to answer of maximum robbery 5, you can either choose to rob that house. If you choose to rob that house, how many gold coins are you accumulating? You are accumulating the gold coins at the 5th house because you're robbing it, right? So you are accumulating the gold coins at the 5th house. Now your problem reduces to finding the best gold that you can accumulate by robbing the first 3 houses. So you get maximum rob 3. This is one option that you have. That was you wanted to rob the 5th house. If you do not rob the 5th house, what is the option that you have? If I do not rob the 5th house, the gold coins that I'm robbing from the 5th house would be 0 because I'm not robbing it. And if I'm not robbing it, am I imposing any constraint of not robbing the 4th house? I am not. So I will just use 0 plus max rob 4. I have these two options. The best answer out of these two options I will take. So I will just say that the maximum out of these two would give me the answer. So either I can rob the fifth house or I can not rob the fifth house, and the maximum of these two would give me the answer. I hope things make sense to everybody here. Let me just very quickly dry run the answer. So I have these houses 27931. So I am defining my state max rob I as the maximum robbery that I can get from the ith till the end. So I want to compute the answer to max robbery 2. So I have two options. So I will say the best answer for robbing the first till the fifth house would be two options, either to rob the first house. If I rob the first house, I will get 2 gold coins by robbing the first house. Plus, I will reduce my problem to a smaller problem of saying, let's now try robbing the third house, because second house can no longer be robbed. The second option that I had was that I can choose not to rob the first house, but I can now try robbing the second house. Does it make sense, everybody? This bigger problem gets reduced to 2 smaller problems. I can now solve this smaller problem M3 in the same way again. I can say either I can rob the third house or not rob it. If I rob the third house, I can say I will get 7 coins. Plus my problem reduces to robbing. This is 1, 2, 3, 4, and 5. If I rob the third house, my problem reduces. So I will get 9 coins. And my problem reduces to checking if I can rob the fifth house. So I will say plus M5. Or I can say that I will not rob the third house, and my problem reduces to finding the best for M4. Similarly for M2, I will say either I can rob the second house, which will give me 7 gold coins. And if I rob the second house, I can now try robbing the fourth house. Or I can not rob the second house and try getting the answer to the third house. Now you guys would appreciate that I need not compute this M3 again, because this M3 would be computed here automatically, right? So I will just compute this once and not compute this M3. So what will I do? I will try computing M5. M5 says you can either rob it or not rob it. I would always want to rob it because there is no house going forward. So this is a base case which will give me 1 gold coin. So 9 plus 1 becomes 10. The second option that I had was 0 plus M4. M4 would again be divided into a smaller problem of either robbing it or not robbing it. I hope it makes sense to you, right? So you start from the first, start dividing into smaller problems, and then you keep on actually going till the base case and making sure that every subproblem is computed only once. Okay? What are the initial values? Initial value for everything would be, let's say, -1. That is, you have not computed it. The moment you compute it, you update the value there. Okay? What would be the base case in this case? The base case would be that when you reach M5, that is the only house that you are left to rob. You would always want to rob it. Okay? So M5 would be equal to 1. This would be a base case. I hope this makes sense to everybody. Right. So let's actually move to the next question. The last question is as follows. The problem is that there is a party going on. Okay, there is a party going on. And the party can be attended by n people. So there are n people who can go to the party. Every person in the party has 2 options. One option is that he or she can enjoy the party all alone by himself or herself. Okay, every person has 2 options. So let's say person I has 2 options, either to enjoy the party alone or to enjoy a party in a pair with any other person. Does the question make sense? There is a party going on. The party can be attended by n people. Every ith person in the party has 2 options. Option 1 is that you can enjoy the party all alone by yourself. Option 2 is that you can actually pair up with any other person in the party and enjoy the party as a pair. Now the question actually asks you that how many unique ways are there for those n people to enjoy the party. Does it make sense? Okay. So which company this question was asked at? This question was, I myself asked this question several times at Direct Eye, and I've seen this question being asked at several other companies as well. So you have to figure out how many different unique ways are there for those n people to enjoy the house party. Okay, cool. So let's actually take some examples. Let's say n was equal to 1. If there is only one person, how many ways that person can enjoy the party? There is only one way. The sad way is that he can only enjoy it all alone. So number of ways would be equal to 1. Does it make sense, people? Now let's say there are 2 people. Example 2 n equal to 2. There are 2 people in the party. Let's say number 1 and number 2. What are the ways that these 2 people can enjoy the party? One way would be that the person 1 is enjoying the party all alone. Okay. And person 2 is also enjoying the party all alone. This is one way. Second way would be that person 1 and 2 have paired up and they are enjoying the party together. Does that make sense? Are there 2 ways here? The answer to this problem would be 2. That number of ways would equal to be 2. Okay, cool. Now let's actually take another example of, let's say, what happens if there are 3 people in the party. If n is equal to 3, how many ways do you see the 3 people enjoying the party? Okay, cool. So 1, 2, and 3, how many ways are there for the 3 people to enjoy the party? Let's actually formulate them. Either all 3 of them can enjoy the party alone. The second option is that the person 1 and 2 are enjoying the party together and the person 3 is enjoying the party alone. Third option is that person 1 and 3 are enjoying the party in pair and person 2 is enjoying the party alone. The fourth option that we have is maybe 2 and 3 are enjoying the party together and 1 is enjoying alone. So there are 4 ways. This is 1, this is 2, this is 3, and this is 4. So number of ways in this question would be equal to 4. Cool. So we have discussed that for three people in the party, there are 4 ways to enjoy the party. Let's now actually try to see whether this problem can be solved using a dynamic programming approach or not. What were the features that we discussed? The first feature was optimal substructure. Do you see optimal substructure here? Let's try to figure that out. Let's say you already know the number of ways 3 people can enjoy a party, which we already know is 4. And let's say we already know the number of ways in which 2 people can enjoy the party, which we already know is equal to 2. Now let's say we know the number of ways 3 people can enjoy the party, we know the number of ways 2 people can enjoy the party. Can I actually figure out the number of ways 4 people can enjoy the party? Can I actually figure that out? To figure that out, do you try to answer the question that what is the element of choice for the 4th person? The 4th person, the first choice that he has is either to enjoy the party alone or he or she can pair up with anybody else. Okay? Other option is that he or she can pair up. If he enjoys the party alone, do you think the problem reduces to the number of ways 3 people can enjoy the party? Let's say we already know the answer to the number of ways 3 people can enjoy the party, which was 4. Now the 4th person comes, and if he's enjoying the party alone, can you just say that just because he's not doing anything but enjoying the party alone, the number of ways would just be number of ways 3 people can enjoy it, and the 4th people joining them and not doing anything, so that's why multiplied by 1. Does that make sense, people? So you can say number of ways 3 people can enjoy the party multiplied by 1 if the 4th person is enjoying the party alone. On the other hand, if the 4th person decides to pair up with somebody, okay, you guys tell me which all people he can pair up with. There are 3 people in the party already. I am the 4th one coming. I decided I want to pair up with somebody. I have 3 options in front of me to pair up with them. Does that make sense, everybody? There are 3 people already in the party. I am the 4th one. I want to pair up. I can pair up with any one of those 3. So what will I do? I will say that I have n-1 options to pair up. So if I'm solving the problem for 4th person, there are 3 ways for me to pair up with somebody. Okay. The moment I pair up with somebody, let's say I paired up with the 2nd person. What does that mean? It means that the 2nd person and I are occupied. We cannot pair with anybody else, but the remaining 2 persons can do whatever they want to. So if you see that whenever the 4th person is coming and he has 3 options when he wants to pair up, if he pairs up with any one of them, now 2 persons out of these 4 people are paired up. So the remaining people that are left are n-2. And if you already know the answer of solving the best answer for n-2, you will just utilize that, which in this case is equal to number of ways for 2 people to enjoy the party. You will multiply that by the number of ways you can actually leave out 2 people, which is n-1. These are the 2 ways that you see. these ways are mutually exclusive and exhaustive, you can just add these two ways to get the answer to how many ways 4 people can enjoy the party. So what did I do? I have just proven that this problem shows optimal substructure, because that is the first feature that I need to prove to see if a problem can be solved using dynamic programming or not. How did I prove it? I assume that, let's say I know the answer for W2. That is, what say if there are 2 people in the party who are enjoying, how many ways they can enjoy. If I know the answer to it, let's say that is equal to 2. If I also know the answer to, let's say, 3 people enjoying the party, which is, let's say, 4, I already computed the answer to these 2 things manually. Now I am trying to utilize these 2 answers to compute the answer for 4 people in the party enjoying. So I am saying, can I actually get this answer using these 2 smaller answers? If I can do that, then I will prove that this problem has optimal substructure. So how do I prove that? I just said that for the 4th person, the element of choice is that he can either be alone in the party or can pair up with anybody else in the party. If that person chooses to remain alone in the party, that actually means that he is just joining the party, not changing any dynamics of the party. The number of ways would still be number of ways for 3 people to join the party. They can pair up, they can do whatever they want. I will just multiply 1 with that, because the 4th person is just going to the party and not pairing up with anybody else, not changing any other dimension, not changing any other part of the problem. The other option that the 4th person had was that he can pair up. If he chooses to pair up, he pairs up with one person. The number of people remaining in the party becomes n-2, which is in this case 2. I already know the answer to that problem, that how many ways 2 people can join the party. I will multiply W2 with n-1, because for the 4th person, he had n-1 options to pair up with anybody. These are 2 mutually exclusive and exhaustive options. What is mutually exclusive and exhaustive? Mutually exclusive means that when you combine all these options together, you are not leaving. These 2 options do not have any common data point in them. So do we think that these 2 have any common thing in them? No, because one says that the 4th person is enjoying all alone. The other says the 4th person is pairing up. So there cannot be any duplicate answer in these 2 options. So these 2 options are definitely mutually exclusive. What do I mean by saying mutually exhaustive? Mutually exhaustive means that there is no data point which is outside these 2 options. Okay? Because the 4th person can either choose to enjoy alone or he can pair up. There is no other option. So these 2 are mutually exhaustive as well. Whenever you see cases being mutually exclusive and exhaustive, you can just add them up to get the final answer. So we add them up, we get number of ways 4 people can enjoy the party is number of ways 3 people can enjoy it, multiply by 1, plus number of ways 2 people can enjoy it, multiply by n-1, and this is how we solve the answer. Okay, we can generalize it and say number of ways n people can join the party would be equal to number of ways n-1 people can join it. So that the nth person is just going and staying alone. So you multiply it by 1. The other option is that the nth person decides to pair up with somebody. If the nth person decides to pair up with somebody, then the number of people in the party that are remaining to be decided is n-2, because 2 people have already paired up. n-2 figure out the number of ways, multiplied by n-1, because the nth person could have chosen to pair up with n-1 people. This is the recurrence relationship that I get. I have just proven that yes, this problem has optimal substructure. The moment I prove that this problem has optimal substructure, recursion can solve the problem for me. To move from recursion to dynamic programming, I need to look at the second feature, which is overlapping subproblems. Do I see the problems being overlapping? Do I see the problems overlapping? Yes, they are. Because when I will compute the answer for wn-1, I will end up computing the answer of wn-2 and wn-3. And here also, if I'm computing wn-2, and here also I'm computing wn-2, why would I want to recompute it? I would just store all these n answers in an array or somehow maintain these states and utilize them to solve my answer. So yes, optimal substructure is also there and overlapping subproblems are also there. So that's why you will now move from recursion to a DP solution and you can solve this problem using DP. Let me do a dry run for this problem. Okay. So let me do a dry run. Before that, let me actually tell you what is memoization versus tabulation. Okay. So I would rephrase this question and ask that this question actually is about what is top down versus bottom up. I explained this briefly, but let me just explain that to you once again. Top down simply means, so do you guys appreciate till this point in time that dynamic programming solutions essentially can be represented as a recursive solution plus doing some memoization. What do we mean by that? DP, I told you, has two features. Every problem that can be modeled into DP has two features. One is that you have optimal substructure. The other is that you have overlapping subproblems. Okay. The moment you say you have optimal substructure, you should be pretty sure that you can solve that problem recursively. Okay, because there is optimal substructure, you can divide a bigger problem into a smaller problem and solve the problem recursively. The moment you see that there are overlapping subproblems, you can go a step ahead of recursion and say that just because the states are being repeated, I would just do memoization, which is nothing but having the values of the answers of those states saved and not computing them again. So that will DP in this way, nothing but a recursive solution, but throwing in memoization. This is something that we call as a top-down approach, that you just write the recursive code and just throw in memoization, because in the recursive tree, you will be seeing a lot of duplicate states. So this is one way of solving a DP problem. The other way is solving a bottom-up approach. Bottom-up approach basically is that you start with your base cases or base case, and utilizing whatever information you have, you compute the answer that you have for the next big state that you can compute. Okay, so using the base case, you compute a bigger answer. Now using all this data, you compute an even bigger answer. Using all this data, you compute even a bigger answer, and so on and so forth. So you are basically not solving anything recursively, but you are writing an iterative solution, that you are iterating from a base case answer and building solutions iteratively as you keep on going with bigger ends or with bigger problems. Okay, this, some people call this as tabulation. What does that mean by calling it tabulation? It means that you just have a table ready with you, which can be a 1D, 2D, 3D table. In every problem that we discussed today, it would be a 1D table, because we discussed 1D DP problems today. What does that mean? 1D DP means that the state, DP state, can be represented with one variable. That is what we mean by 1D DP. Okay, so tabulation means that you just create a table in which you say that these are the states that I want to compute. You fill the values for the base cases, utilizing them. So let's say you fill the values for the base cases, and utilizing them, you compute a bigger answer. Then you compute, utilizing all these things, a bigger answer. Utilizing all these things, a bigger answer, and so on and so forth. So you just keep on filling your table, or in other words, you just do it the bottom-up approach. This is the second way of solving DP problems. So I hope this question should be clear now. Let's now come to dry running this problem. Okay, so let's now come to dry running this problem, and let me actually dry run this problem using the bottom-up approach, because top-down we have discussed very extensively. Let's actually discuss this using the bottom approach and try to dry run it. Okay, dry run the problem of party using the bottom approach. So everybody in the class knew that for n equal to 1, the number of ways for one person to enjoy the party is equal to 1, right? Now, number of ways for two people to enjoy the party is 2. We discussed that one, either both of them can enjoy the party together, or both of them can enjoy the party alone. We also discussed that we know the answer for what if there are 3 people in the party. How many ways can 3 people in the party enjoy? We knew that answer as well. We said that the answer was 4. So now let's say we only know the answer to way equal to 1 and way equal to 2. Now let's say I want to compute the answer for way equal to 3. I've already proven that this answer can be computed. It has optimal substructure, has overlapping subproblems. So DP would be a way to go about it. So what would I do? Now let's say I know that one person is there in the party, and if only one person is there, there is one way. There are 2 people, there are 2 ways. Now the third person comes. The element of choice that this person has, so let me call it E or C. The element of choice that this person has is either to enjoy the party alone or to pair up. If he decides to enjoy the party alone, people, you tell me that the number of ways for 2 people to enjoy the party would still remain, because those 2 are still in the party. And this third person is just going on and tagging all alone. So you will say that the ways for 3 would, in this case, would be ways for 2 people to enjoy in whatever way they can, multiply by 1 because the third person is just tagging along. The other option that he had was to pair up. So what options does he has to pair up? He can either pair up with the person 1 or he can pair up with the person 2. Does it make sense, people? If he pairs up with person 1, how many people are remaining in the party to enjoy? I am the third person. I am paired up with the first person. So he's also busy. I am also busy. Only the second person is remaining. So that would mean that I would reduce my problem to finding number of ways one person can enjoy the party. Similarly, if I chose to enjoy the party, pair up with the second person, then I am busy. The second person is busy. Only the first person is available. That would also mean that there is only one person in the party remaining and there is only one way for him to enjoy. Ways one for him to enjoy. So you see that for pair up, you have ways 1 plus ways 1. How many times are you adding ways 1? That is the number of people who are remaining in the party. So in other words, you can just call this as number of ways one person can enjoy the party multiplied by 2. Right? So what do you do? For 3, you get the answer by number of ways 2 people can enjoy the party, which is 2 multiplied by 1, plus number of way 1 people can enjoy the party, which is 1 multiplied by 2, which makes it 2 plus 2, which is 4. So number of ways 3 people can enjoy the party is 4. So everybody please appreciate how we are tabulating. We started with the base cases, W1, W2. We now came to W3 using those 2 answers. Let me now compute the answer for ways 4 as well. Okay. How can I compute the answer for ways 4? Again, look at the element of choice. The element of choice that I have is the fourth person can either enjoy alone or the fourth person can pair up. If the fourth person enjoys alone, he will say that there are 3 people remaining in the party. Whatever ways they can enjoy, let them enjoy. I will just tag along and you will just multiply it by 1. The other option that he has was to pair up. He could have paired up either with the first person or with the second person or with the third person. If he pairs up with the first person is gone, fourth person is gone, 2 people are remaining in the party. They will enjoy the party in ways 2 ways. What if he pairs up with second person? Again, ways 2 ways. Because 2 persons in the party are remaining. We can let them enjoy in ways 2 ways. 3, if you partners up with 3, again, ways 2. So what is essentially happening? You are multiplying ways 2 with nothing but 3 because there are 3 people in the party apart from the fourth person. So you say for ways 4, my value would be ways 3 multiplied by 1 plus ways 2 multiplied by 3. Ways 3, I already know the answer was 4, so I will say 4 into 1. Plus ways 2, I already know the answer was 2, so 2 into 3. I say 4 into 1 is 4, 2 into 3 is 6. I say there are 10 ways for 4 people to enjoy the party. Okay, cool. So let's now actually come to the last question that I saw. So the second last problem that we had was that there are n houses. You want to figure out the best way you want to maximize your robbery so that every house has some gold coins. You want to maximize your robbery such that the moment you rob a house I, you can no longer rob the house I minus 1 and you can no longer rob the house I plus 1. So this was the constraint that we had. I said, again, let's look at the problem as a combination of, as some states. Okay. So let me define one state for you. Let me define a state which tells you that the maximum coins that you can get. So let me just move it and define a state for you. That is the maximum coins that you can get from looting the first to the nth house. So maximum coins that you can get from looting the first to the nth house. Let's say I want to compute this answer. Does that make sense? I want to compute that what is the let's say I have a problem of finding the maximum coins that I can loot from the first till the nth house. Now I say that to look at this problem, you again have an element of choice. When you are at the first house, you can either to choose to loot the first house, that you can loot the first house, or you can not loot the first house. People, if you loot the first house, do you think you will get some gold coins? If you loot the first house, do you think you will get some gold coins? Yes, you will get some gold coins. How many coins will you get? You will get the coins that were there in the first house. Now, the moment you have chosen to loot the first house, your problem reduces. Your problem says कि ठीक है, earlier my problem was to get the maximum loot from first to nth house. I have chosen to loot the first house. My problem reduces to a smaller problem. What does it reduce to? I have chosen to loot the first house. There is nothing left to loot in the first house. Just because I have looted the first house, I can no longer loot the second house. So my problem reduces to finding the best answer from looting coins 3 to n. Okay. So let me not call it coins I. Let me just call it a reward I. That if you choose to loot the ith house, this is the reward that you get. So reward 1. Reward 1 plus the sub problem of coins 3 to n. Similarly, if you choose not to loot the first house, then what is the sub problem reduced to? If you are not looting the first house, are you getting any loot amount? No, you are not getting any loot amount. So you will just add a 0 to a sub problem. Your problem now reduces to finding the best loot that you can make from the second to the nth house, because the first house you have not looted, and if you did not loot the first house, you can actually still afford to lose the second house. So just by looking at this, you will realize that yes, there is optimal substructure, and I can represent my problem in a recurrence format by this. So if I want to figure out 1 to n, I can say it would be reward 1 plus coins 3 to n, or the best second option that I had was to not loot it and reduce into a problem of coins 2 to n. These are the two options that I had. I want to choose the option which will give me the maximum. So what will I do? I will explore both these options. Whatever comes out to be the maximum of the two, I will return that as the answer. Okay. So now this is the recurrence. This is from 1 to n. Let me just generalize it. So it becomes coins I to j. If I have the house from I to j, I want to loot them. Or let me actually call it I to n, because n is going to remain there forever, the way we have described this problem. Coins 1 to n would equal to, one option is that you actually loot the ith house, you get the ith reward, plus you reduce the problem into I plus 2 से लेकर n तक, or you choose not to loot the house plus coins I plus 1 से लेकर n तक. You take the maximum of the two. Now this is the recurrence relationship. The moment you arrive at this recurrence relationship, you know that this problem can be solved using recursion. Okay, you know that this problem can be solved using recursion. Now, before that, let's actually make sure that we also know the base cases. So what are the base cases? You see that this definition fails to hold true when you are at the last house. Because if you are at the last house, do you think that you can actually go to the n plus 2th house? No, because that house does not exist. So if you are at the last house, that should be a base case, because this recurrence relationship will not be able to define it. So what should be the base case? One base case would be coins n to n. What does that mean? That is a sub problem which says that there is only one house to be looted, nothing else is there. What would be the best answer that you can get? My submission would be, if there is only one house, what should you do? You should drop that house, right? Because there is nothing better that you can do. So coins n to n would equal to be the reward of looting the nth house. So this is one base case that you can see. Now you guys tell me, if I am at the n minus 1th house, will this recursion help me then also? It will not, because if I am at the n minus 1th house, I will be forced to go to n minus 1 plus 2, which will be n plus 1th house. That house does not exist. So even for n minus 1, I should have a base case. So the second base case that I would have would be that what is the best answer for for looting the houses from n minus 1 to nth house. Now my summation is that if you have only two houses, n minus 1 and nth, can you loot both of them? No, you cannot loot both of them. Should you loot none of them? No, you should not loot none of them. At least you should not loot one of them. In fact, you should exactly loot one of them. If you should exactly loot one of them, which one of them will you loot? My summation is that simply loot the house which has the maximum reward out of them. So if the n minus 1th house has the maximum reward, loot that house. If the nth house has the maximum reward, loot that house. So yeah, now you know that you have a second base case as well. Do you require a third base case? So does this problem hold true for n minus 2? Yes, this recursion hold true from n minus 2 house, because from n minus 2 you will be forced to go to n minus 2 plus 2, which is n, and that is still a definition which is defined in this recursion. So that's not an issue. So these two base cases should be sufficient. So till this point in time, we have discussed that yes, recursion can solve our problem. Now you see that a lot of states would be repeated here. If you just solve this using recursion, a lot of states would be repeated. I am leaving that as an exercise for you guys to figure out that how these states will be repeated. I will give you a hint how to figure that out. Just build a recursive tree and see that a lot of states are being computed again and again. So what do? You memorize those states. Okay? You memorize those states. That's it. The moment you memorize those states, you just solve this recursive question, add that memorization, you get the answer. You get that answer top down. If you want to solve that answer bottom up, what do you do instead? You start with the base cases. So you start with, what if I only had the last house? The answer will be reward n. What if I had the second last house and the last house? The answer will be maximum of two of them. Now if I have the answer to these two cases, can I actually figure out the answer from n minus 2 to n? So what I'm saying is, let's say I know the answer if I only had this house to loot, then what would be the best answer? So let me just actually take an example, real life example. So let me take an example and see what would be the answer there. 2, 7, 9, 3, and 1. So let's say I know the answer. This is my base case, right? The last one is my base case. The answer would be that you can get only 1 coin, right? So the answer to 5 would be 1. The second last is also a base case. The answer to 4, as we discussed, would be maximum, that you can either choose to loot this one or this one. Maximum of 3, 1, which happens to be 3. Now you come to this point. If you are actually doing it bottom up, so you have the base cases. Using the base case, you solve a bigger problem that you can just solve using the base cases. So if I have these 3 houses, what is the best thing that I can do? I have 2 options. Either I can choose to loot this or not to loot this. If I choose to loot this, the second option is choose not to loot this. If I choose to loot this, I will get 9 coins because I'm looting it. And just because I'm looting it, I cannot loot the 4th house. So I will be forced to only consider the answer for the 5th one, which I already know this one. So this will be 10. One option gives me answer 10. Second option is I do not loot this house. So I will get 0 coins from this one. But I can still manage to loot the 4th one, which gives me 3 coins. So the answer will be 3. So I take the maximum of 10 and 3. So the maximum is 10. So I know that for this, for answer 3, the maximum answer that I can get is 10. Now using these 3, I can compute for this. Either I can loot it, not loot it. If I loot it, it would be 7 plus answer of 4. If I not loot it, it would be 0 plus answer of 3. Answer of 4 is nothing but 3. 7 plus 3 is nothing but 10. Or you can say 0 plus answer 3, which is nothing but 0 plus 10, which is 10. You take the maximum of 2, which is 10. So you say even for this, answer of 2 is also 10. Now you are left with this one. You again have 2 choices, either to loot it, not loot it. If you loot it, you make it 2 plus. If you loot it, you get 2 coins just because you are looting it. It becomes 2 plus answer 3. Or it becomes 0 plus answer 2. 2 plus answer 3 is 10. Answer 3 is 10, right? Sorry, answer is 10. 2 plus answer 3 is 12. So one option is 12. Or you say 0 plus answer 2, which is 10. The maximum of 10 and 12 is 12. So you say that if for the first house the answer is 12, so now you know the answer that if you want to loot from the first till the nth house, the best thing that you can do is get 12 coins. Okay. So today, what did we discuss? We discussed what is dynamic programming. We now understand that any problem which shows optimal substructure and overlapping subproblems is a problem which can be modeled into a DP solution. We know that the moment a problem shows optimal substructure, it can automatically be solved using recursion because you can divide a bigger problem into smaller problems. Now, the moment apart from showing optimal substructure, it also shows overlapping subproblems. You can essentially store the subproblems answers and utilize them the next time you see them. So now you actually move from recursion and go to a dynamic programming solution. Okay, so DP in one way is nothing but recursion plus dynamic programming, recursion plus memoization, because you see some problems being repeated. Okay, this is one way to look at it. The other, this is the top-down approach. Bottom-up approach would be that if you have proven that you have optimal substructure and overlapping subproblems, start with the base cases, utilize those base cases, and get the answer to the next case that you can get. And then utilizing all this information, get the answer to the next thing that you can get, and so on and so forth. You keep on building your answers, you will get the entire answer. Okay, this is the bottom-up approach that we have. Apart from that, let me explain you some more things. Then we also discussed that how to figure out whether a problem can be solved greedily or not. The problem can be solved greedily if by just looking at something without looking at what holds for you in the future, if you can make a greedy choice, which will always give you the best possible answer. If you can make such a choice, a greedy solution will work. Okay, if you cannot make such a choice, you are bound to explore all possibilities. Then you should think the DP way. How to think the DP way? Look at the element of choice. Look at any element. Look at what element of choice do you have. Either you can include it, not include it, do something with it, not do something with it, and so on and so forth. The moment you look at the element of choice, you can, looking at the element of choice, construct a recursive definition of the problem. You can construct a recursive solution. You can just create a recurrence relationship for that problem. The moment you do that, then you need to figure out, do you see overlapping subproblems in that recurrence? If you see overlapping subproblems, just memorize it, you get a DP solution. So this is just in brief what we discussed today. We discussed several questions today. This was the basic building block class of DP. Stay tuned to Scalar Academy and keep a tab on all the videos that we keep on sharing with you guys. All the very best for everything that you do. Goodbye.
Hello everyone, welcome back to Scalar Academy YouTube channel. Myself Vamsi. In this tutorial we will be solving another most frequently asked dynamic programming question in an interview named coin change. So we will be discussing two solutions. One is a recursion, another one the recursion solution by using the dynamic programming memoization technique. Okay, so without wasting any time, let's get started. So before starting, so if you are visiting channel for the first time, please don't forget to subscribe. So if you like this content, please hit that like button up, and please let us know what do you feel about this video in the comment section. Thanks. First, let us understand the problem statement. Okay, so you will be given an array and it contains a coins. Let's say what are it will be 1, 2, 3, 5. Okay, so these are all the coins and they will give you the target value and integer. Let's say in this case it will be 11. So you need to figure out what will be the minimum number of coins to make this target value. Let's say so you went to a shop, okay, and you gave 2000 rupees and you asked for change. Okay, so now, so if a shopkeeper has given all the 10 rupees coins, like 10 rupees notes, currency, okay, so 10 rupees into 200, so you will get 200 rupees are notes. Okay, 200 notes, like you can say coins. Okay, 200 coins. Now if shopkeeper has given you 100 rupee coins, then it will require 20 coins. 20. If shopkeeper has given you a 500 rupees coins and it will be taking 4, so here 4 coins. So basically there is no 200 and 150 rupees 500 coins, but I'm saying that. Okay, and if like you have given 2000 rupees note, again he gave you 2000 rupees note, okay, then it require only 1 coin, right? 1 coin. So this is what a minimal number of coins, okay, you will get. Okay, so this could be your answer. This is your answer. So a minimum coins, okay, for a given currency. Okay, so let's try to understand for this particular example. Okay, so first Okay, so there are 1 rupee coins, 2 rupee coins, and 5 rupee coins. Okay, and here one thing to understand here is very important. So whenever you are in an interview, you have to ask one question at the first. What is that question? So are these coins are infinite supply? Means infinite supply. Like, so can I get these 1 rupee coins as many times I want? So let's say here, to make 11 rupees a change, you required if you have given 11 1 rupee coins, then it will be 11 rupees. Target sum achieved. Okay, so no, I don't want like that. Okay, so what I will do, I will make 1 into 9 rupees. Okay, like I will give a 9 coins of 1 rupees, then 1 2 rupees coin. Okay, then what happens? It will again 11, target sum achieved. Okay, so in this case totally we have given 11 coins. Now I am counting 11 coins. Now here 9 1 rupee coins and 1 2 rupee coin, so totally 10 coins. So it's great, right? So I will try 2 rupee coins now. Okay, so 2 into 5 are 10 and 1 1 rupee coin. So here 10 and 1, it's 11. So how many coins I have taken now? 5 plus 1, so it's 6 coins. Less than 11 and 10, right? Yes, it's acceptable. Now is there any other way? Let's see. Okay, so still with the 1 and 2 combinations you will be having more coins as well. So like 3 2 rupees coins and 5 1 rupee coins, something like that as well. Okay, and here, yeah, so now let's come to 5 rupees. So can I say 2 5 rupee coins plus 1 1 rupee coin? Totally I have 3 coins now, which is way more better than other solutions, other coins, right? Since I am wanted a minimum number of coins required to get target value. Okay, now so is there any other way that we can reduce this further? Let's keep on trying. Okay, so 1 5 rupee coin and a 2 2 rupee coin, and so 5 4, so 1 into 2, or you can say 2 into 1 as well. Okay, so it will become 4 coins. So I can say that 3 is the minimum coins I required to make this 11 rupees. So this is what an answer looks like. Okay, so this is the answer if there is an infinite supply of coins. Infinite supply of coins. What if there is only one coin is supplying to you at a time? Okay, so let's see the given coins are 1 2 and 5, and you're required to make 11. It's not required. It's quite greater. So if you add all these as well, you will get only 8 rupees. It's not 11 rupees, right? So you can't make at the change of 11 rupees. So how can you do? Let's say if I have given you a 6 rupees, like you need to make change for 6 rupees. Now how many minimum coins you require? So if you consider all the 1 coins, then 1 into 6 coins. If you required a 3, then 3 coins. 5 into 1 plus 1 into 1 are 2 coins. So this is, can I say at max you require 2 coins if I am giving a finite and I am searching for target 6. Okay, so but in this like tutorial I will be discussing infinite supply of coins. Okay, so I am pretty much sure that after finishing this entire tutorial, watching this entire tutorial, you will be able to solve this limited number of coins supply on your own. Okay, just give it a try. Okay, we catch up with another tutorial where I will be explaining with limited number of coins as well. Okay. Now I hope you have understood the problem statement clearly. So now I recommend you to please pause the video, think for a while. Okay, so I will give you a hint as well. Okay, so think in a recursive manner. Recursive manner. Okay, just think in recursive manner. So let's start. Okay, so I'm following a top-down approach. Top-down approach means where I will be starting from last index and moving towards the starting index. Means if I have array of size like coins of size 10, I will be starting at 10th element, and I will move keep on moving till the last element. Okay, first element, sorry. Okay, that's how top-down approach of recursive works. Okay, so now let's see. So let's stick to the example that we have now. So the array, the coins are 2, 1, 2, 5, and the target value is 11. Okay, so let me point out the indexes 0, 1, 2. So what is the last index? The last index is 2. So I will be starting from a second index. So here I'm considering parameters or my index and a target value. Okay, let's say I will be having a function called a coin change. Let's name this as a CC for our simplicity, and I will be starting at 2 and I'm searching for 11. Okay, this is what my initial state looks like. Now tell me, so I'm currently here. What is the decision can I make here? So can I say if okay, so 5 is less than 11? Yes, hota, like happens, right? So 5 is less than 11. So can I say, after seeing this particular thing, can I assume that to make the change of 11 I can have 5 in that thing? So secondary is like forget about rest of the elements, just think about this 5. So can I include a 5 in my 11 coins? Yes, I can, right? So 5 is less than 11, so I can include that. Okay, so I can include that. So CC, and so my current sum will be going to be a 6, right? So I'm searching for 11 initially, and I have included a 5 in it. Okay, and I have reduced that target sum to the 6 now, because I have reduced that 11 minus 6. Okay, done. Now tell me, so I can take that if I don't wish to take that. So I'm not interested in taking that a 5. Yes, right? So that's my choice. Okay, so let's assume you are a shopkeeper and you have all the 1 coins here, 2 coins here, and 5 coins here, like infinite, and you have to give the change of 11 rupees. So it's your take whether you can take this 5. So yeah, I wanted to give only 1 rupee coins to the guy. So so that's a decision of shopkeeper. Okay, so he can give 2 rupees, he can give 5 rupees, he can give 1 rupee as well, but at the end of the day it is his choice. Okay, so that is what we have to stick. Okay, so here this is called a take, this is called not take. Okay, so take means you are considering that particular value into your change, and not take means you are not including your that particular value into your sum. Okay, now so if you have included this, okay, you have included this particular 5 into your target sum. Now tell me, so since it's an infinite set of you have infinite coins. Okay, so here you will be having all the coins. Okay, all like 1000 infinite coins. So if I am making it a choice of, like, if I wanted the change of 10, I can give all the 5, right? All the 5, 2 5s, that is possible, right? So in that case, though if you have considered that particular value, you can again consider that value. So here, do I need to move to my next index? No, I can stay there only. And again, I can check whether that particular value is again included after including one time, and again I will check whether that can be included or not. Okay, so I will stay in that second index only. Now this is the case of if I not take, I don't wish to take this 5. Okay, then my target will be 11, and so if I'm not interested to take this 5, I can move to next index, right? So I will make my index as 1. Oh, I hope you guys have understood. Okay, let me tell you. So here what I am doing, so if let's say coins of index less than target, okay, so less than target. So if this is the case, what I'm doing, okay, if this is the case, what I'm doing, so either I can take or not take. Okay, if I'm taking this, I'm doing this, like I'm subtracting that particular coin from my target sum, and I am again staying back there only, because I have to make the I have to include, I don't know whether again that value can be included or not. Okay, and if I don't wish to take that kind, I can simply just move on. Okay, so my target sum will be target sum only. Okay, so here if I consider that if you take that particular coin, what you need to do, you need to increase your coins, right? So I will simply return 1 plus. Okay, if you wish to take that coin, you have to increase 1 value. So samajh ho gaya. Now let's go. So again you are standing that particular thing. So now second index, and you have a target of 6. So 5 is less than 6. Yes. So again what you can do, you can take that value. So 2, and if I take that, I am standing there itself, and I am making the sum as 1 now. And if I don't wish to take that, so it will be 1 and 6. Now again, so I'm standing at second index, and I'm aiming for target 1 now. So 5 greater than 1, right? So I want the change for 1 rupee, and you are showing me 5 rupees. That is not sufficient, like it's exceeded, right? So you must not include that. So what you will do, so can I say, so if 5 is not included, there are some other coins which might include, right? So what I can do, I can simply, I won't take that. Okay, I won't take that. I can just move to another indexes. Okay, which is a CC of 1. So at 2's next 1, and again target of 1. Yes, here I have only one choice. Okay, I wish not to take that. That's it. Okay, now I'm standing at 1 index, and I'm searching for 1 value. Yes, 2 greater than 1. So I may not include that. I have only one choice here. Now again what I could do, 0, 1. So I am standing at 1 rupee coin, and I'm searching for 1 rupee target sum. Is that the fine? Yes, I can include. So which is a less than or equal to. So I can include. So 1 plus. So I have taken that. Okay, I have taken that 0, 0, right? And if I don't wish to take that, CC of -1, and my sum will be -1 only. Okay, so now tell me, my target sum became my target coin will become a 0. So I got it means that I got the change for what I'm looking for. It means that I got the change what I'm looking for. So I will simply return 0 here. Okay, will simply return a 0 here. So you have written 0, and 1 plus 0, it's a 1. So you will return 1 here. You will return a 1 here. Now you have seen a negative index. Okay, since you have seen a negative index, what you need to do? Okay, so basically since you are you want minimum number of coins, so you can return something a max value like int max or 1e9. So if you are returning 1e9, it might get overflow, so just do -1. It will, oh yeah, like that happens. Okay, now you will consider minimum of these both, right? So minimum of these both, and you will return 1. So 1, and here you will return, so you have only one option. Okay, so you will return 1. Okay, to this thing. Now 1 plus 1, it's a 2. 1 plus 1, it's a 2, and you will go up, so it will return 2. So from left side, okay, you got 3, right? So 1 plus, sorry, from left side you got 2. Okay, from left side you got 2. Let's see here. And you are currently standing at this particular 1th index, and you want the sum of 6. So 2 less than 6. Yes, so it means that you can take that guy, cc of 1 comma 4. Or you might not, you are not interested in that thing, so you will just move down and you will keep that sum as it is. Now again you are standing at here. Since you have considered this, you have to make +1. Okay, now you came here, and again, so you are standing at 1 and you want the sum of 4. So 2 less than 4. Again you can consider that 1 plus cc 1 comma 2, and it's your decision, you are not interested in that, so 0 comma 4. So again you came to left side and you will solve this, and you are currently standing at 1th index, means at 2nd coin, and you want the target of 2. So again it's a less than or equal to, it's an valid thing. So 1 plus cc and 1 comma 0, and here your sum target sum became 0, so you will return a 0 here. 1 plus 0, it's a 1, so you will return 1 here. So 1 plus 1, it's a 2, so you will return 2 here. 1 plus 2, it's a 3, so you will return 3 here from a left side. Okay. Okay, so did I forgot something here? So it's your wish as well, like here. Okay, so if you wish not to take this, it will be 0 comma 2. Okay, so if you are standing at 1, okay, so if you are standing at 1, if you consider this, and you can take up that, so cc of 0 comma 1, and if you wish not to take cc of 0 comma -1 comma 2. Okay, so it will return int max, since you have reached negative index. Okay, and again you will go here, and you can again consider that cc of 0 comma 0. Okay, so it will, since you have reached a 0, it will return 0, and 1 plus 0, it's a 0. So 1 plus 0, it's a 1, sorry, it will return 1, and 1 plus 1, it will become 2. Yep, so minimum of these two, it's a 2. So minimum of this 1 comma 2, it's a 1, so you will return 1 plus 1, so it will be 2. And so you need to solve this. Let's say you so you are currently standing at 0th index, and you wish to solve this as a 4. Okay, so means that you have 5. Okay, so you have a 1 rupee coin. Currently you are at 1 rupee coin, and you want to make the change of 4 rupee. So that is possible, right? That is possible. So you will say cc of 1 plus 0 comma 3, and if you wish not to take that, it will be cc of -1 comma 3, 4. So it will return int max. So you will go this state, cc of cc of 0 comma 2. So 1 plus, sorry. So again it will, if you wish not to take this, cc of minus 1 comma 2. So if you wish to carry on and 0 comma 1, and you are currently standing at 1 rupee coin and you want 1 rupee change, and so again if you wish not to take this, and it will return minus 1 comma 1, so it will return int max. Here it will return int max, and you will go again. So here again you can stand at 1 plus cc of 0 0, and you wish not to take up this, and minus 1 comma 0, so it will return int max. It will return 1. So since we have reached some 0, it will return 0. So 1 plus 0, it's a 1, so it will return 1. So 1 plus 1, it will be 2, so it will return 2. So again it's a max and all. So it will be a 1 plus 2, it's a 3. So yeah, so int max of 3, a minimum of 3 comma int max, so it will be 3. So 1 plus 3, it's a 4. So here 4. Okay, so 2 comma 4, it's a 2. Okay, minimum is 2. So here 1 plus 2, it's a 3. Okay, so again you need to traverse on this side, so I'm not making this. Okay, so it's already a mess. Okay, you can, I hope you have figured out what is happening here. Okay, so give it a shot. Okay, you will get to know. So we are doing only three rules. Okay, I will, let me summarize those things. Okay, so before moving on, let's assume it has something written, and again minimum will be 3 only. We know that answer is 3. So anything, so I'm pretty much sure that nothing was less than 3, so I will return simply 3 here, and here I got a 2. Okay, so 2 is minimum, so 1 plus 2, it's a 3, so it will return 3. So not take, if you go on carry on this, anyway you will get 3 as minimum, so it will return 3 as your answer. So this is how it looks like. Okay, so a big tree. Okay, because you will be having a lot of combinations here. That's why, because you will be having infinite supply of coins, right? That is the reason why you have this big recurrence tree. Okay, so let's go and try to code this up. Okay, let me summarize what we have did so far. Okay, so basically we have a function called a coin change, where we will be having a index, and a coins means it's an array or a vector, and this is an integer, and you will be having an target value. Okay, again it's an integer. Now you will be entering into this particular function, and first, so what will be our base case? Figuring out the base cases. First thing, sigma rule in recursion. Okay, so base cases. So can I say my first base case would be, what if my target equal to 0? What if my target equal to 0? Can I say simply return 0, because I don't require any coins, right? So to make the sum of 0, target of 0, I don't require any coins. That's a simple one base case. And next, so what if, so since I am starting my index at the max thing, so what I can reach, so till I can reach index less than 0. So whenever my index less than 0, it means that I have reached a negative index. So can I say whenever I have seen a negative index, I can simply return int max. So because I'm aiming for minimum answer, so I'm returning int max. So anyhow it will be going to be and not in my answer. Cool. And yeah, these are all the 2 base cases. Okay, base cases. Now our actual logic comes here. Now first thing, so it has passed these both. Now what you need to check? So you need to first check the coin which you're currently standing is less than the target or not. Means, let's say you have a currently a coin of 5 rupees and you want the sum of a 4. Okay, your target is 4. Now obviously you can't include 5 in that particular answer, like target, right, to make that target, right? So what you can do, so let's say whenever coins of that particular index greater than target greater than target, then you can't include that coin. So simply what you need to do, you just need to go to another coin. So simply return coin change index -1 coins amount. That's it. So what if this is false? Okay, so coins is less than target, less than or equal to target as well. Then what you need to do, you need to include that in your answer. That is one choice. Okay, so it is less than. Okay, now means like you are currently standing at 2 and you want the sum of 4, target of 4. So it is possible. Now it's your choice to whether to take that answer in to take that 2 coin into your 4 or not to take that coin into your 4. Okay, so let's say I will have 2 variables. Okay, 2 variables. Let's say int take. Okay, so if I take that coin, I must need to keep track of that, right? So 1 plus, I just need to increase my coins. So 1 plus coin change. If I include that coin, now what I need to do? So since I have infinite supply of coins, I need to stay there itself. That is what we have seen in recurrence tree, right? So I will be staying there. I'm not increasing or decreasing my index. I'm staying there only, and my coins are coins, like so. Whatever I got the coins, I will be supplying that. And so if I consider that into my answer, means a target, I just need to make that target minus coins of index. Agree? So if I include that, I have to remove that from my target, right? Then only I can make it that to a 0. So our agenda is to make that target equal to 0, and whenever we have assumed a target is 0, our job is done. We have found the choice, like change. Okay, this is for take. So what if I wish not to take? Then what I need to do? So I don't need to increase my coins. So I will simply call coin change. If I wish not to take that particular coin, I have to go to next coin. So index -1 coins target. I'm not taking my I'm not considering that particular coin. That is the reason why I'm not doing subtraction that particular coin from my target. So after making these 2 recursive calls, what I need to do? I need to simply return minimum of take comma not take. Agree? Done. So yeah, so did we figure out all the cases? No, I don't think no. Why? So let's say if you are in an interview, you have to ask this question in the beginning. Okay, so let's say my target is 1000. Let's assume 1000, and I have given you coins of 0 1 1. Okay, let's assume 1, or let's say okay, so let's change this. Okay, so I have given you a target of 3 rupees. Okay, target of 3 rupees, and I have given you these coins of 2 rupees. I've given you only 2 rupee coins, and you need to make the target of 3 rupees. Now, is that a possible? No, that is not a possible, right? So if you take 1 2 rupees coin, it will be -1. Okay, still you need a 1 rupee coin, and if you take a two rupee coins, you have like you are giving 4 rupee change, not 3 rupees. Okay, so as a shopkeeper I am getting lost. Okay, so I am not interested in that case. Okay, so in that case our answer will return int max. Okay, so int max, it will return int max. So okay, so it's your interviewer choice what to return. Okay, so whether he wanted to return something like not possible or something. Okay, it's interview choice, but mostly they will say return -1. Okay, if there is no particular answer, you can't make the choice for the, like, you can't make the change for the given target, just return -1. Okay, so in this scenario I will return a -1 in my like main function. Okay, so now that's it for the code. Okay, so let's quickly go and uh, write the code for this particular approach. Now let's try to code the approach what we have discussed so far. Okay, so the input format for this particular thing would be you will be given a first n. Okay, and you will be given then target, then you will be given set of coins. Okay, so it means n, target, and a vector. Okay, now let's try to accept that input. So int n and target, and you require a vector of this size, let's say coins of the size n. Okay, and you need to accept them. N coins of yeah, that works. So till now we have accepted the input. Now we need to process our answer. So let's assume we have a function called coin change, and it is accepting index, coins, and target. So here we are passing index as n-1, then coins, and then a target. Okay. Now let's go and code this particular function. Okay, in a coin change of let's say index, and then we are passing a vector as int coins, and then int target. Okay, first our base cases. So first base case is whenever our target is equal to 0. Whenever our target is equal to 0, simply we are returning 0. Okay, so whenever our target is 0, we are simply returning 0. If our index are less than 0, so index less than 0 means, and we have seen a negative index, then what we need to do? So as we have discussed, we are returning an maximum value. Okay, so here the maximum, so I'm not considering int max, let's say at 10 power 9. Okay, so if we return 10 power 9, in some cases it might get into the overflow. Okay, so you can do -1 simply. Okay, now this is our base cases. Now what is the first case? So what if our current coin is smaller, sorry, large, greater than what? Greater than your target. So if it is greater than your target, you must not include that. Instead, you have to go to another coins. Okay, other coins. So if coins of index greater than at the target value. then simply return coin change. You have to go to the next index, means you are currently at index, and then if you have to go to the next index, then it will be -1. Then it is a coins, then it is a target, so you are not including that value, so that is why you are keeping the target as it is. So if this is not the case, means it's a less than, so it's like current coin is less than target. So if it is less than target, it means that you can include that or you can not include that. That's your choice. So let's say int take. Okay, I can take that value or I cannot take that value. Okay, that's depends upon the choice. So if I include that value, okay, let's say I have decided to take that coin. So then what I need to do? So I have to include that. I have to increase my count, right? So coin change. And again, do I need to go back to the next element or do I need to stay back here itself? I need to stay back here itself. Why? So I have infinite set of coins, right? So though if I consider that particular coin for the target, I have to check again whether I can make another coin of this particular target coin this as well. So that is why I will stay at this particular index only. Then coins. Now what I need to do? So I have taken that coin. Okay, I have taken that coin. If I have taken that coin, what do I need to do? If I have taken that coin, what do I need to do? I need to include, I have to decrease that particular coin. Right? I have to decrease that particular coin. Done. So if I have decided not to take up that coin now, not taken. So now what happens? So I may not increase my coin value since I have not taken that. Instead, I have to go to the next index, right? So if I decide not to take current value, then I have to go to the next value. Then coin. Since I have not taken that value, my target will be as it is. Now at the end, what I need to do? I need to return minimum of taken and not taken. So this is what a algorithm looks like. Okay, so I'm hoping this would return our answer. Okay, now so we are getting our answer in answer variable, and so here we need to make a corner case where we will be returning, like where we will be not having enough coins to make the current change. Okay, so then what it will return, our algorithm will return 1e 10 power 9 minus 1. Okay, so if answer not equal to 10e power 9 minus 1, so it means that there is some suitable guy. Okay, so I can make the change. So in that case, I can print this answer only. So if not, if my current answer is 10 power 9 minus 1, then I can simply print a minus 1. Done. So yeah, yep. So let's so for this input, I'm expecting output as a 3. Let's try to run this code first and then we'll see. Since it's recursive and the complexity of this approach would be exponential, it is taking a lot of time. Okay, so it given 3. Okay, let's check out for failure, like where it will be not making not have enough coins to make the change. So I have a array size of 1 and I'm looking for 3, and the current values I have is 2. Okay, now save this and let's build this solution. It will return answer very quickly this time, I guess. Yeah, so we got -1. So why it has written answer very quick? because so we have very less number of cases to check for. So yeah, that is what a time complexity means, why time complexity is so much important. So yeah, so it is returning correct answer. Now let's try to analyze the time complexities of this particular approach. Yeah, so it is definitely going to be exponential. Okay, so why, how exponential? So I'm making a two function calls here. Okay, so it is at like at max, in worst case I'm making two function calls. Okay, then it will be 2 power something. So what is that something here? So can I say what are all my changing factors here? So target and index and target. So can I say I'm finding all the possibilities of an current index and the target. So in that case, in worst case, it would be index into target. But if we have here infinite set of coins, since we have infinite set of coins, it that the time complexity of this particular approach would be greater than 2 power index into target, because we have infinite set of coins. Since you have seen that recursive tree as well, it has a lot of recurrences. Okay, it has a lot of recurrences. Okay, I have stopped at the middle, but it has a lot. Okay, so yeah, if you are in an interviewer then straight away ask you to optimize this particular solution. So how to optimize this? So what you can see here, so I can see I'm repeatedly solving the problem which I have solved previously. Doesn't make sense? Yeah, it makes sense, right? So let's see. So let's figure out something. So here CC of 0, 1, and again I am solving CC of 0, 1 here, and again I am solving CC of 0, 1. Again I am solving CC. So it's repeated, like repeated, right? So 1, 4 again, and so yeah, 0, 0 everywhere, 0, 0, and again I will be having 0, 0, 0, 0. Okay, so I'm solving the same problem again and again. So can I say it has optimal substructure subproblems? So and so whenever there is some cases where I will be doing same task repeatedly, like same task more than one time, in that case I can say memorize. I can memorize the answer. So memorizing answers can be comes under dynamic programming. Okay, so how can you convert this particular logic into the dynamic programming? So basically, let's say so first you need to figure out what are all the changing factors here. So index and target are the changing factors here. Index and target. So you have to create a 2D matrix with the size of index into target. Okay, so let's say simply a vector of a vector int dp n into vector of int target. Initially let's assume I'm initially filling it with -1. Okay, now so what I can do, I can pass this dp here. Okay, I can pass this dp here, and whenever I am returning my answer, so not simply returning the answer, so before returning answer to my main function, I can say store that in my state, dp state. So what will be my dp state? So dp of index of target. So I will store that answer into this particular state. So that is how I will do. So wherever I am making recursive calls, I will do that. So here again I am considering the answer. So in dp of int and target equal to min of take comma not take. So here before entering into this logic, like right after the base cases, I will include a check here whether I have solved that particular combination, like so 0, 0 cases, like in where index is 0 and target I'm searching for is 0. So such cases. So whenever I will check here, okay, so like dp of index of target, so not equal to -1. So if that index, like that particular state has not doesn't have -1, it means that it has some value, it has already computed. So what I will do, I will simply return that answer. So dp of target, done. Yes, this works. This is what a memoization means. Okay, so memoization means you will be having your recurrence code, and you will be simply just converting that code to dynamic programming by simply adding your dp states over there. Okay, so let's go and code this particular solution. So we are not writing code from the scratch, so we will be just doing some modifications here only. So the first modification here is you need to create an two-dimensional vector dp of size n into size of target. So I'm filling it with -1s. Okay, and I need to pass this as my argument. Then if I'm passing as my argument, I have to catch that in my parameter as well. Yeah, so wherever I'm making call, I need to update the as always. So here dp, here dp. So whenever I am returning something, so before returning, I just have to store that in my states, dp states. So dp of index of a target. Okay. So then yeah, so I need to check here. So check for previously solved current state. So if a dp of index of current target not equal to -1, not equal to -1, means that simply return that answer. Yeah. Do we need to forgot anything? No. Okay, so let's save this, and so let's try to change our inputs. So 3, 11 and 1 to 5. So I'm expecting 3 as my answer. Okay, so we got something bigger here. We got something bigger. Uh, 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 yeah, so here, so yeah, we need to include a target +1. Why? So if we are searching for target 11, so we have to assign the space of we have to assign the states till 11, right? So if we want till 11, we need to give the array size as 12. So that is the some silly mistake I did. Let's try to run this code again. Yeah, done. So we got this output, and yeah, so it works fine, I guess. So give it a try. Okay. Yeah, now let's try to analyze the time complexity of this particular approach. So basically, if you are in an interview, if you come till so far, it's fine, because I have seen this problem in a couple of platforms as well. The cases are not that much bigger, like maximum, like target will be maximum of 12, and the end will be maximum of 10. Sorry, not 10,000. Okay. it's a 10 power 3 or 10 power 4 at max. Okay, this particular DP solution. Okay, so the time complexity of this particular approach would be okay, it would be like n into target. Okay, and space complexities, since we have written memoization code, it will be taking extra stack space. Okay, plus we have taken the 2D dimensional vector, two-dimensional vector with the size of n into a target. Okay, so that is the overall complexity of that particular approach. So that's all for this video. Okay, let's catch up in the next video.
So hello everyone, welcome back to Scalar Academy YouTube channel. So in this tutorial we will be solving another most frequently asked interview question named longest common subsequence. First of all, we will be discussing about approach of this particular problem, and then we will be writing the recursive code. Then we will be optimizing that recursive code using dynamic programming. When I say dynamic programming, we are using two techniques, both are like memoization and tabulation. So please watch this video till the end. Okay, so if you are visiting channel for the first time, please don't forget to subscribe. If you like this video, please hit that like that button, and if you have any queries, please let us know in the comment section.
So the problem statement will looks like this. Okay, so you will be given two strings, let's say s1 and s2. Okay, let's say a b c d e, and another string as a b d e x. Okay, so as you can see, the length of the strings might differ, okay, from each other, and both are not same. Okay, and you need to figure out longest common subsequence. When I say subsequence, what does it mean? Okay, let's say, so in this example, let's say, so a b and b, so here the whatever the order, okay, let's say a and b are matching. Okay, so the next element is a d. Okay, so where does that d exist? So right after b, right? So not in order, but yes, it has occurred after b. Yes, here. So now e, again d after, so x, there is no x here. So the longest common subsequence was a 3 here. Now let's take another example. Say x y z a b c, and here b a c. Okay, b a c. Now what is the longest common subsequence here? B and b. Okay, 1. Okay, fine. And here, so both are here ba and here ab. So these both are not subsequence. Okay, these both are not subsequence, but individually this can be a subsequence, right? B alone can be a subsequence, a alone can be a subsequence, right? Now let's take c. Okay, c here, c. So c is alone is a subsequence. Yep. So by combining bac, we do have any subsequence? No. We do have any subsequence with bc? Yes, 2. And we do have any subsequence with ac? Yes, check 2. So the longest subsequence that for this particular example was 2. Okay, hope you figure out. Okay, let me tell you another example as well. Let's say a b c, and another one was empty. Okay, now tell me what is the longest subsequence here? So obviously 0. Okay, hope you have understood the problem statement. Okay, now pause the video for a while, come up with an brute force approach, what you can think of. Okay, I will give you an hint. Okay, think in an recursive manner. Recursive. Okay, yep. Let's start. Okay, so we'll be discussing 3 approaches. Okay, 3 solutions for this. Okay, so basically 2, one with a recursion, another one with a dp. Okay, so when I say dp, it is both a memoization and a tabulation what does this memoization stands for. If you don't know what is a memoization, that's okay, fine. I will tell you, I will give you a glance about it. Okay, so a memoization means you will write a recursive code. Hope you know recursion. You will write a recursive code. Okay, so you will be trying to memorize the answer which you have already computed. Okay, so basically we will be having a few concepts like overlapping, subproblems. Okay, I will tell you what is overlapping subproblems are during our discussion, okay, of recursion tree. Okay, we'll try to avoid that particular problem. So that is what DP stands for. Okay, so using the pre-computed value or already computed value to compute the current values. So that is what simply DP stands for. Okay, and we will be doing this with the recursive code only. Okay, we won't write any loops here. Okay, but when it comes to tabulation, we will be writing a loops. Okay, so basically it's an iterative code. Okay, yep. Well, this is a glance, and again I'm using a top-down recursion. So it can be done both bottom up and top down, but so it's your choice. Okay, what you can come up with. Okay, so after watching this video you can do both things. That's not a big deal. Okay, I will tell you. Okay, I will write in code as well. Okay, for both of the things. So without wasting any time, let's get into the solution. So first, recursion solution. Okay, I will write one example here for our recursion tree. Let's say let me tell you, I will pick up my name Vamsi. Okay, and let's say ASX. Okay, so I will write, let me write sizes as well, indexes. Okay, these are all the indexes as well. Now I will try to make an recursive tree. So if you don't know what is a recursive tree, okay, I highly recommend you to watch my previous video which I have made on recursion. Okay, so that you will get a glimpse of what is the recursion tree, how to make that recursion tree. Okay, so in this video I will be just going through the solution. Okay, so a recursive tree means it's like a steps. Okay, it contains all the steps, how I am traveling through the particular like how I am traveling through entire solution. That's it. Okay, in simpler case. Okay, so let's say I'm assuming I have a function called LCS, and I will be passing my indexes where I have to start from. Okay, since I stated already I'm using a top-down recursion, so I will be starting from the bottom. Okay, like start in the end. Okay, so the indexes are 4, 2. Now, okay, let me change my string to here I as well. Okay, so instead of 3 I will say 4, 3. Okay, now tell me, so I and I both are equal. So here we will be having different cases. First case is caret both indexes are same. Okay, so both character values indexes are same. So here, okay, I will write the cases while solving the problem. Okay, so as of now we have encountered one case, so that is both the characters are same, so I and I. So it means that it might be my it might include in my subsequence. Do you agree, everyone? Yes, right? So now what I do, so I have to move forward. Yes, I have to simply move forward both of my pointers. Okay, so I will make my index as LCS of 3, 2. Done. Okay, now cool. So now let's see S and X. So is both are same? No. So the case here was, second case was not same. Then what we need to do? So if both are not same, what we need to do? So let's say here. So if I increase my if I decrease my pointer from 2 to 1, 2 to 1, so I'm not decreasing my Vamsi's pointer. Okay, it is still staying at 3 only. I'm just decreasing my second pointer, which is from 2 to 1. Now both are forming one subsequence. Yes. Okay, cool. So it means that I am saying that, so I have to move only one, either of the one. Okay, so in this case it is I'm moving second pointer. So in some cases I have to move my first pointer as well, right? So here I will be having two conditions. So either move first pointer, second thing, either otherwise, or move second pointer. So there are the two choices I have. So basically, when I say TP problem, it's all about choices you are going to make. Okay, so now what I am doing, so first I don't know what exactly happening over there, so I will just keep on trying all the possibilities I have. Okay, so what are all the possibilities I have now? I have two possibilities. One is move my pointer up, pointer 1 down, or I have to move my pointer down. Okay, so let's say first I will move my first pointer to the right. Okay, so already I am at 3 and 2. If I move my first pointer, it will be 2, 2. Okay, so if I don't wanted to move my first pointer, I have another choice called move my second pointer, which is 3, 1. Earlier I am at 3, 2. I have to move to 3, 1. Okay, done. As of now, clear. Okay, now let's see. So I am at 2 and 2. So M and X. So both are same, and no, both are not same. Again, I have two options. What are all the options? So I can either move to the right. Okay, so I move my pointer 1 to the right. Let's say if I move that 1, 2. Otherwise, LCS of 2, 1. Now again. So now again. So 1 and 2. 1 and 2. So A and X. Both are same? No. Again, I have two options. LCS of 0, 2. LCS of 1, 1. Done. So next. So again, so 0 and 2. Yes, 0 and A and X. Both are not same. Yep. So again, I have two options. -1, 2, or 0, 1. Done. Okay. Now I have came here. Now tell me. Is there any index called a -1? No. No. We all know that indexes last from 0 only. So whenever I have came to index less than 0, there is nothing. Okay, simply I will say return 0. Okay, return 0. Cool. Return 0. Now I have only this substring. I will go and traverse through this. Okay, so 0 and 1. So both are not equal. V and S are not equal. Again, I have two options. LS of -1, 1. LS of 0, 0. Okay, so again I came up with -1. So there is nothing here. So I will simply return 0. And here 0 and 0. So A and V and A. So both are not equal. Again, I have two options. LCS of -1, 0, or LCS of 0, -1. So in both the cases, I will return 0 since I have reached -1 or -1. So if either of the indexes are -1, I have to return 0. Okay, now done with this and done with this. Now what next? So here I am returning some values here. So which one do I need to consider? Let's say in one of the subtree, okay, either right or left, I got one subsequence. Since I am looking for the longest subsequence, what I can do? since I'm traveling from the end, or if you're, it doesn't matter if you're starting from the start as well, doesn't matter. So if I got any subsequence, which one do I need to return? So I need to return a max of 0, anything, right? So I'm pretty much sure that in one of the ways I will definitely reach a 0, right? If one of the ways I will definitely reach 0, because that is a base case, that is what you will end up with. Okay, so if I get anything at the right hand side which is a greater than 0, or let's say 1 and 2 as well, so I have to consider longest, so I need to consider a max. So here I will return max among both the subtrees, right? Max among both the subtrees. What is the max among both? So 0. Okay, I will return 0 here. So again 0 and 0, I will return max, so again it's a 0. Now it has max, okay, so 0, so it will return 0. Now I have to solve this particular subsequence. Okay, yeah, there is no space at all. Let's see. Okay, so 1 and 1, so A and S both are not equal. Yes, LCS of 0 1, and another one was LCS of 1 comma 0. Okay, so we know the answer of a 0 and 1, right? Like here, so we 0 and 1 both are not equal, so it will return 0 only. Okay, since we have computer, since we don't have much space, I'm just utilizing that. Okay, so 0 and I will return 0 here. In this case as well, 1 and 0, did we computed that? No. Okay, let's see. So here 1 and here 0, so A and A both are equal. A and A both are equal. It means that you have to compute 1. Okay, you have to return 1. You got something, right? So it means that we have to make another call with 1 plus LCS of, you have to decrease both, you have to move up forward, like you have to compute down. Okay, so a 0 and minus 1. Okay, so we have seen a minus 1 in one of the cases, so we will return 0 here for this thing for sure. Okay, so 1 plus 0, it's a 1. Okay, we will return 1 here, and our right side 0, left side 1. So what I told earlier, you have to return the max, right? So you will return 1 here. So here you have 0 and here you have 1, so you will consider max 1. Now let's go and solve this particular problem. So 2 1 1, what is a 2 1 1? As a 2 M and 1 as S. Okay, so let me draw that to LCS of 2 comma 1 here. Okay, sorry. Yeah, now so let me write the indexes 0 1 2 3 4, 0 1 2 3. Okay, so 2 1 1, M, yes, both are not equal, so I have two options. What are the options? LCS of, I can move a left, so 1 comma 1, and I can do LCS of 2 comma 0. Now if I do 1 and 1, so 1 1, A and A, sorry, A and S both are not equal, so what I can say? So I can again move either left, I can move again either right. Okay, so 0 and 1, again both are not equal, so LCS of minus 1 comma 1, LCS of 0 comma 0, so it will return 0 since you have no minus 1 index. Okay, now again 0 and 0 both are not equal, so you will return a 0 again, so top is a 0. Now you will go on this side and 1 and a 0, so both are equal, so you will return 1, and you will go to our next index 0 comma minus 1, so we have seen minus 1, so again it will return 0 only, so that's why I have directly written minus 1 here. Okay, sorry, plus 1. Okay, sorry. So now again max among these was 1, Now I will travels through this LCS of 2 comma 0, 2 comma 0, M and A. So both are not equal. So what you will do? So you will decrease these things. Okay. So LCS of 1 comma 0, LCS of 2 comma minus 1. Okay. So since you have seen minus 1, it will be returning 0 only. And here 1 comma 0. So 1 and 0. Yes, it has seen S1. So it will return 1. So max among these 1 and 0 are 1. So max among these was 1. So it means that LCS of 2 comma 1 is returning 1. Returning 1. So here LCS of 1 comma 2 returning 1, LCS of 2 comma 1 returning 1. So max among these was 1. So you will return 1 here. Now your job is to calculate for 3 comma 1. Okay. 3 comma 1. Okay. Let's go and see this. LCS of 3 comma 1. So 1C. Yeah. Is that this? Oh, okay, sorry. Yes. Okay. Now, so 3 and 1. So 3 and 1 not equal. So what are the two choices you have? You can either move left or you can move right. Okay. Okay. Now, so 2 and 1. 2 and 1 both are not equal. Again you have two choices, LCS of 1 comma 1, LCS of 2 comma 0. So 1 comma 1 not equal. Okay, again you will be having two choices, 0 comma 1 both are not equal. So you will say again you will be having two choices, LCS of 1 comma 1 and LCS of 0 comma 0. Okay, so since it has seen minus 1, there is no index called minus 1, so you will return a 0 here. And 0 comma 0 both are equal? No. So you will return again 0 here. Okay, sorry. Okay, you will make another choices, minus 1 or 0, LCS of 0 comma minus 1. So since you have seen minus 1, you will return 0, a 0. Okay, so max among this was again 0, so it will return max a 0. Now you will compute 1 comma 0. So 1 and 0, so both are equal, right? A and A. So you will be having only one condition called both decrease of both. Okay, and you will have plus 1 as well. And here 0 and 0 both are equal and no, so you will be having again two conditions, minus 1 and 0 and 0 and minus 1. Okay, so since it has seen minus 1, you will return 0 and 0. Okay, so it will again return max, so it will be 1 plus 0, it is again 1. So 1 max of 0 comma 1, it will return 1 only. Now 2 comma 0, LCS of 2 comma 0. So I think we have already computed that. Okay, he is returning a 1 only. Okay, so I'm simply gonna make it 1. So max of these things, it will 1. And let's say LCS of 3 comma 0. So did I computed that already? Did I made okay, so LCS of 3 comma 0, 1C A S X I. Okay, so 3 and a 0 both are not equal. So again it means that I have two options, LCS of 2 comma 0, LCS of 3 comma minus 1. Okay, since I have seen minus 1, I can simply say return 0. So now let's compute for this LCS of 2 comma 0. Okay, so 2 comma 0 m1 a both are not equal. Yes, I have again two choices, LCS of 1 comma 0 and LCS of 2 comma minus 1. Okay, so 1 comma 0 both are equal. Yes, both are equal. So I will return a 1 plus LCS of 0 comma 0, sorry, 0 comma minus 1. So since it has seen minus 1, I will simply return 0. So it's a 1 plus 0, it's a 1. Now I have seen minus 1 here, so I will return simply 0. So 1 plus 1 max of 1 comma 0, it's a 1. So it will return 1. Now a max of 1 comma 0, it's a 1. So it means that LCS of 3 comma 0 returning 1. Okay, it is returning 1. Cool. Now it means a max of it will return 1 only. So it means that here it will return 1. So here, what is the max here? So it is saying that both are equal, and it means that it will return 1 plus max among these. Sorry, yeah, max among these, it's a 1. Right, it's a max among these were 1. So it will return 1 plus, already we have 1, so it is a combination, right? 1 plus 1, it's a 2, and here again you will be having 1, so it's a 3. So that is what the answer says to that, right? ASI is a subsequence. Okay, now so we have seen all these recurrence relations. It's a little mess, yeah, little mess here, so but it's okay. Okay, so we'll now try to remember the steps. I hope you guys are remember the steps, and now we'll try to write the recurrence relations and convert that into the recursive code. Okay, we'll convert that into the recursive code. Code. So what does it looks like? So basically, let's say we have LCS function, okay, where we will be having taking n and m, so which are both the starting. So what will be our base condition? So whenever we have seen anything less than 0, 0, we are saying that return 0. So done. This is our base case. Is there anything that we are stopping? No. Now if this is not the case, we are checking with either like S1, so string 1 n double equal to string 2 of m. Basically I'm checking both the characters. So if this is the case, what I am returning? I'm returning 1 plus LCS of, I'm decreasing both the indexes, right? N minus 1 and m minus 1. This is what I'm doing. Now else. So else I have two algorithms. What is move left? So I'm considering the left subtree. What is the left subtree? So I'm decreasing my first string pointer. Okay, I'm not adding anything. So LCS of n minus 1 comma m. I'm putting that my second index pointer at the same place. Okay, and I'm moving. And in the right, I have another option called in the right LCS of. I will be sticking at the same in this string 1, but I am decreasing my string 2 pointer. Yes. Now at the end, after this computing these things, what I am doing? I'm returning max of left and right. Done. So in the whole process, this is what I am doing. Yes, this is our recursive code. Okay, now let's discuss the code. Okay, let's try to code the what we have discussed in the solution. So first you will be required to accept the input which is two strings. Okay, so Cn S1 S2. Okay, then you need to have the length of both these strings. So let's say it's S1 dot size and S2 dot size. Now you need to compute your answer. I will be storing that recursive answer in my solution answer. Then LCS of n minus 1. So why n minus 1? Since if you have computed size, let's say if it contains a five characters in the string, then the index would be n minus 1. So since I'm starting right start for like end from end of the string, it will be n minus 1, then m minus 1, s1 and s2. So at the end you will print that answer. Let's try to go on, create the function called LCS. So it will return int. Okay, it will return the longest common subsequence, and you will be taking n, then string s1, string s2. Okay, first you need to write the base cases. What are the base cases? So if either of my indexes are less than 0, if either of my indexes are less than 0, I need to say return a 0. That will be my base case. If this has been not the case, I have to consider case 1. So if you have remembered, we will be having two cases. First case is when my string, like character, both the characters are equal. So if both the characters are equal, what I am doing? So I will just return 1 plus. I'm moving both my pointers down at the same time. n minus 1, n minus 1, s1 and s2. If this is not the case, what is the case 2? So just return. You can consider you will be taking a left. So left subtree. Okay, what will be the left subtree? So I will be moving my first pointer down. It means that n minus 1, and I'm keeping my m same at the same position where I'm currently now. So m s1 and s2, and I'm moving at my right a subtree LCS of n comma n minus 1 s1 comma s2. So at the end, what I'm doing, I'm just returning max of these left comma right. So this is what I'm doing, right? So let's simply try to run this code. Okay, so yeah, let's do some inputs a b c d e, and second one was a b d e. Okay, so the expected answer would be 3 here, right? So yeah, the answer is building. Hope we will get the answer. So I'm unable to see any errors though. Yeah, this answer is 3. We got it. Now let's try to figure out the complexity of this particular approach. What will be the time complexity first? So here, so we'll be having 3 loops, but it's an if and else. So I'm pretty much sure that either of the block will be get executed. So and you have to consider the max scenario. So let's assume you have been calling always 2 calls. Okay, so left and right. Then you will be having 2 choices. Okay, for each combination you will be having 2 choices. Okay, how many combinations you have? Okay, so let's say when I say combination, so you will be having, let's say, n as 5 and m as 3. Okay, so how many index combinations you have? Can I say 0, 1? Can I say 0, 2? Can I say 0, 3? Then 1, 0. Then 1, 1. then 1 comma 2. So for each and every number you will be having 3. So for such that you will be having n into m into n combinations. It means that the complexity of this particular approach would be 2 power n into m, 2 power m into m. So you will be, for each and every combination you have two choices. Either you have to go, you can go left, you have to go right. Okay, you will be moving both, and you are saying this is not right and this is right. So you are computing like that. So can I say that overall complexity of this approach as big O of 2 power m into n? Yes, I can. And what will be the space complexity? So we are not using an extra space, but we are using an auxiliary space called stack space. As you all know that recursion takes a stack space. So what will be the stack space here? So that stack space is again big O of 2 power m into n. That many combination that we are trying, right? So is that a like since it's an exponent, this is not an accepted solution, so the interviewer will ask you to optimize that further. So whenever you have written an recursive solution and you have to optimize that solution, then you have to remember one thing: you have to do that with a DP first. Okay, DP. So if you don't have much time in an interview, and if you felt there are some other solutions as like BFS or any greedy approaches that is lower than a dynamic programming or recursive, then you can go ahead and explain it, because basically explaining DP like solutions to an interview it takes a lot of time. It will kill a lot of your time. So I recommend you to directly jump into another solution if you have any other solutions in mind. Now here we don't have any other choice, so we have to do it with a DP. So we have recursive code. So now I will tell you how to convert this into DP simply. Okay, that approach is called a memoization technique. Okay, I will tell you that. So what is a memoization technique? So basically memoization means like, let's say, so let's see first so whether we can do this problem with DP or not. So I will tell you that when can we go with DP. So as you can see here, I have highlighted few things. So LCS of 2,0 and 0,0. So again, what you can see, so I am computing LCS of 0,0 2 times here. So are you pretty much sure that I am computing only 2 times? No. Let's say, so I am computing 0,0 here. Okay, and if I go up again, I am considering computing 0,0, right? Do I need to compute these many times? No. So the answer of 0,0 was 0 at any time, because V and M were not matching. So whenever I have computed 0,0, the answer would be 0 only. Okay, so for that, do I need to compute that many times? No. So now think, okay, imagine if something happens like this. So whenever I have computed, I have solved some sub problem, okay, I will keep that in my memory. Okay, so whenever again I have asked me to, okay, I have asked my machine to compute that particular problem again, so my machine knows the answer. Okay, what my machine can do, it can simply return the already previously computed answer. So this is called a DP. This is called an DP. So how can we achieve DP using these recursive calls? Okay, so I will be first telling the memoization. Let's take a vector of vector. So before moving into that, so how much space that I need to assign? So that will be my first question. So how much space that we need? So here for that you need to observe what are all the changing factors, like changing indexes. Okay, what are all the values changing in your recursive code? So here my changing values are m and m. So it means that I need to memorize this both. I need to keep that in my memory. Okay, so if so here or two values are changing, I need to consider two-dimensional array or vector. Okay, so if a three indexes like three values are changing, then I need to consider three-dimensional vector or three-dimensional array. Okay, if one index is changing or one value is changing, then I can consider a one dimensional array. So here two, so I will consider two dimensions. So vector of vector dp of n into m. So I will be initializing that with the -1. Okay, so why -1? Let's say I'm putting that -1 as my empty space. Okay, empty space. I haven't solved any problem yet. So whenever I'm my particular space, my particular problem is not -1, it means that I can say that I have the solution for you. Okay, so I will simply return that. That's it. So I need to pass here dp as well as my parameter or argument. I will go top and I will implement it in my now so wherever I'm making a function calls, then I have to make here and here. Now what I need, so here let's say if dp of n m not equal to -1, not equal to -1, then return dp of n and m. So I'm returning, so where I'm storing the answer. So here let's say, so instead of returning your answer directly, what you will do, you will store that in your answer. Okay, so like someplace, okay, at your indexes, then you will make a call to the next one. Okay, so this is how a memorization solution looks like. Okay, so let me simply change my inputs, then let's try to run that code again. So here let's say bd. Okay, bd. So now I'm expecting 2 as my output. Okay, let's save this and build this solution. Finished, and we haven't got the answer as a 2. It is giving, okay, it is saying that there is some error. Cool, have forgot. Got out as 2. So this is how we can convert our recursion solutions to the dynamic programming solutions. So now let's try to analyze the time complexity and space complexity of this approach. Okay, so what we did, so basically earlier we are making a particular call so many times. So we have reduced that and we have memorized the answers to compute only once. Now tell me how many combinations that we have. We have n into m combinations, and how many function calls we can make now. We can make, can I say we are making only m into n combination like function calls? How? Let's say I have made a function call once, like let's say 0, 1, and I have computed that and I have stored that answer in my memory. Okay, whenever I am going to compute that 0, 1 again, it is going to tell me you have already computed and take this answer. Okay, so in that case I'm reducing my function calls, so I'm computing only m into n, exactly all the new combinations, all the unique combinations. Okay, so so the time complexity of this particular approach would be big O of n into m. Now coming to space complexity. So we are creating two-dimensional vector. This size of n m, okay, n into m. So n rows and m columns, so n into m. So the space complexity of this approach will be big O of n into m plus. Since we are making again recursive calls, it would be again, so how many recursive calls we are making? We are making big O of n into m. Okay, so yeah, so it's bro, we have converted our solution to the dynamic solutions. Is that enough? No, I guess so. As you all know that recursive solutions are not that much efficient as it seems, okay, because it is using auxiliary space called like stack space. Okay, so can we avoid that extra recursive like stack space? Yes, we can. How? Converting like writing iterative dp called a tabulation. So just keep this code in mind. Okay, I'm not using anything apart from this. I will be just writing these steps again, okay, but simpler manner. Okay, let's try to write the tabulation method. Okay, so again we will be required to create a two-dimensional array of n plus 1 size this time. 0. Okay, I'm initializing all with zeros. Then I require two for loops starting from 1 each. And if my s1 of I equal to s2 of a j, means that if my both the values are equal, what I need to do? I need to store dp of j equal to 1 plus dp of I minus 1 and j minus 1. Yes. Now else, if this is not the case, what I need to do? I need to store this a max of dp of I minus 1 j comma dp of I and j minus 1. So at the end I will be printing C out of D of n and m. So now let's see, the expected answer would be 3 for this particular output, and let's say yes, so we got 3 only. This correct. Okay, so now let's try to analyze this time and space complexity of this particular tabulation method. So here it's very clear. Okay, so n into m, so we are using two for loops, one with size of n and one with size with m. So it's simply m into n. Apart from that, we are not doing any extra computations here. So the time complexity is big O of n into m. Coming to space complexity, we will be creating two-dimensional vector with the size of n into m, okay, at max. Okay, so the space complexity would be big O of n into m. So are we creating any extra space? No. Or are we have any stack space here? No. Okay, so this is the difference between memoization dp and tabulation dp. In some platforms, if you submit memoization dp solution, it won't accept because as you all know that it's an stack space, it consumes stack space. So if you could submit this tabulation method, it will accept. So you can see, right, so there is nothing much differences between both the solutions. Okay, both are, everything is same. Okay, both are same. Okay, no need to worry about that. You can easily convert your memoization solution to the tabulation method, and if you could submit this tabulation method, it will get accepted. Okay, done. So happy coding. See you in the next tutorial.
Hello everyone, welcome back to Scalar Academy YouTube channel. Myself Vamsi. In this particular tutorial, we will be solving another most important dynamic programming interview question named edit distance. Okay, so the problem statement and the solution and all the optimized approach we will be discussing in the video. So I highly recommend you guys to watch this video till the end. Okay, so if you are visiting channel for the first time, please don't forget to subscribe. If you like the video, please hit that like button up, and please let us know in the comment section how did you feel about this particular video.
So now let's discuss the problem statement. Okay, so the problem statement will go something like this. You will be given two strings. Okay, two strings. So let's say S1 and S2. Then you need to figure out. Okay, you need to figure out total number of operations. Total number of operations that you require to convert S1 to S2. Okay, so the operations that you can perform were insert, delete and replace. Okay, and each operation takes one, let's say cost of 1. Okay, cost of 1 each. So I hope you got the point. Okay, let me just try out few cases. Let's say I have given you a string, two strings, as S1 as Sunday and S2 as a Saturday. Okay, now you need to convert your Sunday to the Saturday. Okay, that operations that you can perform is either delay, insert, delete, replace. Okay, now let's say what is the one way that you can convert this Sunday to Saturday? So I will just insert all these things. Okay, like I will, instead of having S, A, then T, then U, then R, then A, then D, then Y. Yes, I can do this. Now tell me how many operations that I have made. So I have replaced U with the A with the U. Sorry, I have replaced U with the A, then T, then U. So at each time, so all these were replace operations, and these two were insert operations. So this is one possible. So here the total cost was 7. Yes, 7 operations. Now what is another possible that way I can do? So let's say here, instead of I decided to, okay, so here I have a day, right? Yeah, I will keep that day and I will change these things. Okay, I will delete these 2. Okay, or I will replace. Okay, let's say I have replaced this 2 with A, T. Now I will insert U, R. Now tell me in total how many operations that I have made. I made 4 operations, which is a way more less than the 7, right? Yeah, it is also valid. Yeah, and again, and what is the next thing that I can do? Let's say this is the best. Okay, so just check. Okay, what are all the possibilities that we have? So S matches. Okay, let me write this Saturday as well. Yes, this S and this S matches. This D, this D. Yeah, good. And I have U, and yeah, I have U. Now I will replace this N with R, or yeah, R. Now I am done with all these things. Now I have these 2. I will insert them. Okay, yes, A, U, A, T, R. Now in total, how many operations that I have made? 3 operations. Can I say out of 3, 7, 4, like all the possibilities, 3 is the one which took minimum, right? So 3 is the minimum. So you should return 3. Got it? Got it? So yeah, I hope like it will give you a good picture if you try out with other possible examples on your own. Okay, so now please pause the video for a while. Now think about the solution that you can come up with. Okay, so let's continue. So here I have taken jam and SM. Now I wanted to convert this jam to the SM. Okay, now let's say what is the one thing that I can do? Insert. So where I need to, so currently my indexes are here, means at 0 comma 0. Okay, so so whenever I made an insert, it will looks like something like this. Okay, S A M and S M. Okay, now I have this S and S first sure. So since I have inserted the same number, I'm pretty much sure that S will have, means this second S2 the index which I am currently. So now I just need to go the next character, right? So which is M. Yes, so now currently I am staying at 0 only yet. So this jam, so basically we are not inserting. Okay, we don't care about the values, we just care about the number. So we are not just inserting, but we are just for assumption I am writing S. Okay, so still we have made one operation, okay, plus 1, and we are still just checking whether this J will match with other characters, other set of characters. Okay, now again we are at this is one kind of operation. Let me finish all this. Okay, so delete. So delete means, let's say we are J and S are both are not equal. So I'm saying that just delete this guy. Okay, so if I delete that, it will become A M and SM. Right, if I am deleting, means I'm not deleting from this string. Okay, I'm just moving ahead, means I will be moving my S1 pointer to the plus 1, means a next index. Now here I am not moving my J, means second S2 string wala pointer. Okay, now means it is replaced. So replace wala means, so I'm just replacing whatever I have this here, I'm replacing with this whatever I need. Okay, so in that case I'm pretty much sure that if I replace them, I know that both these things will match. Okay, then I don't need to do any task. So I will simply say AM and M. Done. Hope you have understood. Okay, if you haven't, please pause. Okay, please go back and watch the again. And here now here comes the picture again. So yeah, so again 3 options: insert, delete and replace. Okay, so insert, so we are currently at J and we are currently at S. Now again I can see that yes, sorry, we are currently at J and we need to increment here. Okay, sorry. So we have made a progress in insert. Okay, so J and M are not equal. So again we have 3 options. So what is the first option? I can insert it. So if I insert that, it will become, again it will stay at J, then it will go to the point where I have nothing. Okay, so nothing. So whenever it has seen the size of the element, okay, whenever it has seen the size of the element, so I should return the set of characters which are available in the rest of the string. Okay, so here I have reached the size of 2, okay, which is my S2 size. So now I am currently standing here only. So to make these changes, okay, so I need to process the three characters. Now how much cost it will need to change all of those? Can I say 3? Yes, right. So what is that 3? Can I say that S1 dot size minus whatever the size here we took? So it is saying, now let's say here, let's assume that it is J. Whenever we have made J, then wherever we are currently, means we are currently at this particular J. So it requires S1 dot size minus I. Okay, if we have, if suppose if we have reached S1 end, okay, S1 end, then it would be S2 size minus J. Okay, whatever the leftover characters in the S2, we need to process all of them. That's it. Okay, so here this is about insert. If we are making an delete, so we are just deleting that J, so we'll make a process to the next guy. So it is going to be A M, and again it's an we will be staying at the same, so we are staying at the M. Okay, we are staying at the M. Now then it's a replace, so I will replace this particular guy J with the one which I want. So it is going to be A M, and I will, if I replace that, I will move to the next thing, right? So if I move, there is nothing. Now how does it cost me? It will cost me around the size, okay, the size of this particular string minus where I am currently standing. So here I am currently standing at the first index, and the total size is 3. So 3 minus 1, it's at 2. Yes, right? To make this string completion, I need 2 more operations, either delete or insert or replace, whatever, right? So this is how you will process the particular tree. Okay, so this is going to be very big. Yeah, so that's why I'm not making. So I hope you have understood. So because we have watched like we have did a lot of problems. Okay, so if you haven't watched, please try it on your own and go and watch my previous videos where I have discussed plenty of problems. Okay, and let's see here. Cool. So let's see, right, let's try to write the code. Okay, where are we starting from? We are starting from the 0, means let's say we are having a 0 0 and S1 and S2. So this is what we are passing, and here we have a function which catches all these things. So let's say solve. Now what is the first character, like first case that we are going to handle? Let's say whenever my I becomes S1 dot a size. Okay, whenever my I becomes S1 dot size, then what do I need to return? I need to return whatever the set of characters I have in my S2. I need to return all of them, right? So let's say, so I need to return S2 dot size minus J. Okay, and if my J reaches the end, then I need to return S1 dot, like whatever the set of characters, okay, I have in my current string, like remaining. Okay, now these all the cases that we need to handle. Okay, now what if, okay, what if 2, okay, let's say I have seen S and S, then I need to just move on to the next character, right? I don't need to do any operation. So because they are equal, okay, whenever they are equal, I don't need to do anything. Okay, so I don't even need to increase my count, right? So I can say that S1 dot I double equal to S2 dot J. So when this is the case, just return like just make a call, okay, call by improving, like by moving on to the next pointers. Okay, S1 S2, done. Now if this is not the case, then you need to traverse, then you need to pursue the other 3 options. First one is insert. Okay, like what is the insert kind of thing? So it is, you are staying currently you are not moving S1. Okay, you are not moving, so S1, you are only moving your J1, means the second string pointer. Okay, then S1 S2. Cool, this is the insert, and the next is delete solve. Here you are not making the you are moving only in S1 string, because you are deleting that guy, right? You are deleting that, so you need to check the next guy with the that pointer which you are standing in the S2. So I plus 1 comma j S1 comma S2, and then next one is a replace. So what are you doing in replace? Okay, if you remember, we are just staying there itself, like we are moving on to the both pointers. We are moving both pointers. For delete, we are moving only first pointer. For insert, we are staying in the first pointer at the same position, but we are making progress in the second pointer. Okay, so for replace, solve I plus 1 j plus 1 S1 S2, done. So out of all these points, like, so you for every operation you require 1 point, right? For every operation you require 1. So what you can do, so return 1 plus, so you need to consider the one which gives you the minimum cost. So minimum of insert, delete, replace. Yes, done. This will give you the output. Okay, this is just an recursive code, so still we need to convert this into the dynamic programming. So now let's simply go and try to convert our code. Yeah, so what is the thing that you need to require first? So you need 2 strings, so S1 comma S2. Then you need to take them up from the board. Yeah, then let's say int answer equal to solve I plus 1 0 comma 0 S1 and S2. Then you need to print answer at the end. Okay, let's go and make a function called solve. So you will be accepting I, then j, then string S1, then string S2. So the base conditions would be like, if I is if I is reaching to the end, then you need to return the set of character, like you need to compute the set of characters which were left over in the second string, right? So S1 dot size minus the point where you are currently, done. And if you have reached your second pointer to the end, then you need to return the strings which are left over in the first guy, right? Done. Now if not, if you haven't reached both ends, then you need to check whether I equal to j. Okay, so if this is the case, then return solve, just make a progress to the next set of characters. Okay, I plus 1 j plus 1 S1 S2. So if this is not the case, then you need to go with other options. Okay, what are all the other options? Insert, delete and replace. So when you are talking about insert, you are just moving your second pointer to the next. Okay, S1 and S2. And delete. Okay, let's say delete. Okay, so solve. So here you are making progress in the first string, but wherever you are in second string, you will be there only. Okay, and our last one is replace. So here you will be making progress to in the both of the strings. Okay, then at the end return 1 plus minimum of all these operations. It will give us the output. Okay, let's try to see. Okay, so let's say I have given a jump. So here it requires two operations. One is replace either J or M, either J or A with the S, and delete the other one. Okay, so it requires three operations at the minimum. Sorry, two operations at the minimum. Let's execute this. So solution building is taking some time because complexity is too much. Yeah, so we got the 2. Okay, so yes, it works. And if we wanted to convert the same to the dynamic programming, how can we do that? So very first thing that you need to do in dynamic programming is while you are converting your recursive solutions to the dynamic, then you need to first observe what are all the positions that you like, what are all the things that are keep on changing. So here I and j are keep on changing, so you will make a vector of 2D. The sizes of s1 dot size, then a vector s2 dot size, filling with the -1. Now wherever you are calling, just pass dp over there, and let me copy this. Then so yeah, here you are again calling. Then here now before checking with the character, just make sure you check in dp as well. So I j not equal to -1, just return dp of I and j. Okay, so before returning your answer, just store and return. I hope this makes sense. And let's try to change our inputs to the Sunday and Saturday. So we required 3 as our answer. So let's see. Yes, we got 3. And yeah, so it will work. Okay, so the time complexity of this particular approach is going to be m into n, and time space complexity is also m into m, and but it uses some extra space for the stack. So you guys know what to do to reduce that stack space. So if you want me to do that as well quickly, we can do that. Okay, so for that, let's remove this piece of code, but you require dp, right? Yeah. Int m equal to s1 dot size, and int n equal to s2 dot size. Okay, and instead of, yeah, so let's store this with zeros. And okay, so we require int I is equal to 0 less than m and I. So here let's replace it with m plus 1, and plus 1. Okay, so we require 2 for loops. Now let's see what is happening over here. So since it's a bottom up, okay, just tell me. So whenever you are standing at the your I is equal to 0, okay, now you require, so to compute the other strings, how much of time that you require. So do you require the cost of j, right? The number of operations that you required is cost of j. Yes. If, like I'm saying that if I is equal to 0, okay, just make your dp of ij equal to j. Right? That is what we did over there. And else if j equal to 0, then how much cost you require? We require the cost of I. And else if s1 of I minus 1 equal to s2 of j minus 1. Okay. So if this is the case, what you need to do, so your dp of ij will become dp of I minus 1 and dp of I minus j minus 1. Yeah. So else, so this is not the case, and for all other cases you need to store the one which is very minimum in the all the options that you have. Okay, what are all the, with the adding 1. Okay, so dp of I minus 1 j, so this is one option that you have, and next one is going to be I and j minus 1, and another option is going to be I minus 1 and j minus 1. So this is it what we are doing in memoization as well. So at the end we will simply count dp of m and dp of n. Okay, and let's change our input to the something like a b c d e and c d e, okay, or c d j, okay, c d g. So here how many operations that we require? So we required these two. Okay, so and we more required either either you can replace e with the j, so that is one operation, and you can delete these through. So at max you required 3 operations, right? So let's remove this. Okay, so let's save this code. Okay, let's save this code and we'll run it. Yeah, it has some okay. We got the 3 as our input. This is what we expected, and this is how the code looks like, and you can easily compute the time complexity here. So if you see, we are using 2 for loops, okay, with the cost of n into m, and we are not making any stack space here since it's an iterative solution, and the time space complexity is going to be only m into m. Okay, so this is all about edit distance, and yeah.
Hello everyone, welcome back to Scalar Academy YouTube channel. So in this tutorial we will be talking about one of the famous problem, okay, so named 01 knapsack. So first we will be discussing how to approach that particular problem, then we are drawing recurrence relation, and we will be writing the recurrence code, then we will be optimizing that recursive code using dynamic programming memoization technique. So please watch this video till the end, and if you are visiting channel for the first time, please hit don't forget to subscribe. If you like this video, please hit that like button up, and if you have any queries or if you have any video suggestion for us, please let us know in the comment section.
So there will be a thief, okay, thief, and he decides to rob one house. Okay, rob one house, do some robbery. Okay, and we all know that whenever a thief going for a robbery, he always carries one bag. Okay, bag. So we are calling this bag as a knapsack. Okay, knapsack. Okay, simply, and bag is a knapsack, and we all know that it has some capacity. Okay, bag will have some capacity. Okay, and yeah, now let's come to this house, items, right? So let's say a laptop, a mobile phone, a fridge, and let's say TV. Okay, so yeah, it works. Now if there are some items, we all know that it will have some weight as well, right? Weight. So let's say a TV has a weight of a laptop has a weight of 3 kgs. Okay, so mobile phone 1 kg, fridge at 10 kgs, a TV 5 kgs. Okay, and so let's assume a thief has stolen these particular items and he has to sell it. Okay, he will sell somewhere. Okay, and after selling he will get some profit. Okay, he will get some money for that particular item, right? So we will give in that amount as well. Let's say, so if you sell this laptop, you will get let's say 100 rupees. Okay, and if you sell this mobile, you will get 20 rupees, and if you sell this fridge, you will get 500, and if you sell this particular TV, you will get 50 rupees. Okay, and so these are all the inputs you will be given. Okay, so you will be given weights. Okay, weights of items, and profits of items, and a capacity of knapsack, means capacity of a bag. Let's say here, let's stick to, okay, so here you will be given 3 inputs. One is a weight, profit, and capacity of a knapsack. Now you need to figure out the maximum profit that you can products. Okay, so let's say now you have decided to rob. Okay, so now your capacity is 14. Just think, try to answer. If you what are all the products if you get, like if you still rob, okay, you will get some maximum profit. Okay, so let's say if you rob this a TV, okay, if you rob a TV and mobile phone, okay, your weight will become 4. Okay, still you have a 10 left in your capacity, and you decided to rob this 5 kg one. Okay, now tell me what is the your profit so far. So 100, 20, 50, so it will be 170. Okay, so if you sell these guys, like if you stole this 3 kg wala, 1 kg one, and 5 kg one, you will get 170 profit. Now is that the maximum? No, no, right? So now what is the maximum? Okay, so let's say if you have pick up these at 10 kg wala, okay, and still you will be left with 4 kgs. Okay, and of course you can't this 5 kg one won't fit in your bag because you have only 4 capacity, and you decided to rob this 3 kg wala, then you will get 100 profit. Okay, so 500, 100, and then still you have 1 kg capacity in your knapsack, so you will decided to get this 1 kg one, so you will get a profit of 20. So in total you will get 620 rupees. Okay, if you rob this particular horse. So this is what you wanted to do. Okay, and I know you might have one doubt. Okay, so yeah, so let's say, so if you are in an interview, you have to ask this question. So let's say, so in first thing, Okay, you have robbed this two and this one. Okay, and total weight you have consumed 9 kgs and you got a profit of 170. Still 5 kg was left in your bag, right? So can I say I will rob. Okay, so there's a fridge now, so which is capacity of 10 kgs, so I will cut it off so that I can get it for 5 kgs and I will rob that. So I will take that so that I can make 250 profit. Yeah, no, right? So you can't do that. Okay, you can't do that, right? So yeah, that is also not valid in this case. So you have to either pick up that whole item if you have that much capacity in your bag, otherwise you should not pick up that item. That's it. So that's why it is called as a 0-1 knapsack. So 0 means you should not pick up that guy like item. 1 means you can pick up that whole item. That's it. Okay, and there is another problem, okay, which allows you to break that particular item and you can carry that. So that is called as a fractional knapsack. Okay, so there is a separate problem for that. So after finishing this problem, please go ahead and try to complete that particular problem as well. That is easy. Okay, little man. Okay, if you have solved this problem. Okay, so now pause the video for a while and think about this solution. Yeah, so let's first discuss what can happen, like what are all the things I can do. Okay, so let's say I have here, so I will pick up one small example. Okay, so let's say my weights are 1, 2 and 5. Okay, and I have profits which has a 10, 20, a 30, and I have a weight of or capacity which allows me for 6. Okay, which allows me for 6 kg weight. Now you have to figure out what will be the answer for this particular input. It is 40. It is 40. Okay, so let's try to break this problem down. Okay, so first we'll try to solve this using a recursion. Okay, then we'll go to the dynamic programming. Okay, so first recursion. So again I am following top down approach here. Means first I will be starting with recursion, then I will be converting into memoization technique. Okay, so I will be starting from the last. Okay, the indexes would be 2, 1, 0. Okay, for simplicity I am assuming I have a function called a knapsack. Okay, and I have started from the end, so index would be 2 and I am passing my weight as 6. Okay, now tell me what are all the things I can have here. What are all the things I can have here? So can I say so let's say my weight is 6, which I am looking for, and currently I am standing at 5. So can I take that particular item into my bag? Yes, right? So I have a capacity of 6, and if I now am standing at one item, if I pick up that particular item, it will consume 5 kgs, like 5 capacity in my bag. Okay, and still I will left with 1 kg. So I'm good with that. Okay, so I will take that guy. Knapsack off. So here you are permitted to take that particular item only once. Okay, so in house there will be only one item na. Okay, there will be having only one fridge, one TV, one laptop, one mobile, like mobile phones can be multiple. Okay, so So if you pick up this particular guy, okay, so if you have pick up this particular 5 wala, then you have to consider the profit of that guy. Okay, you have to add that particular profit. So you will say 30 plus, and since you have pick up second guy, you have to go to next guy, so which is a 1. And what is the amount of weight you are left with now? It's an 1, right? So initially you have a 6, now you have a you have taken 5 and you have left with 1. So now this is what if I take that thing, if I take that. So if I wish not to take that item, though it is sufficient in my bag, I wish not to take up that guy. Okay, now what happens? So knapsack of I have to move to next guy, next item, and my weight remains same. Yes, my weight remains same. Now what we need to do? Now let's go and solve this particular sub problem again. So let's say again you are solving for 1 and 1. So you are currently standing at a weight 2, and but your capacity is only 1. Now tell me, what are all the choices you have now? So can you take can you take that particular item into your bag? No, because you have only 1 kg left in your bag. But if you take this particular item, it requires 2 kgs. So it is not allowed. So you are left with only one option, that is called not take that particular guy. So here we will say simply go to a next item. So 0, 1. Without any without touching your capacity of bag. Now so again, now I will go here, my index is 0, so the 0th index is 1, right? So 1. Now the weight you are looking for is 1, and the weight which you are currently, if you pick up that guy, is 1. Okay, it's allowable. Okay, so what you will do, you will say what is the weight profit? So 10 plus knapsack of -1, like we have to decrease that -1, and it will become 0. And this is what if you take that guy. If you should not, like if you decided to not take up that guy, it will become -1, 1, right? Now tell me -1. So index you have to come till 0, but you have seen -1. So you will simply return a larger value or smaller value. You have to return a smaller value because we are looking for maximum output. Okay, so you have to return a minimum value, okay, which might be like any negative value or int min. Okay, int min. Or if your problem statement stated like, so if you are not pick up any, like if you are not allowed to pick up any guy, okay, let's say where you will be having case your capacity is 10, and the items all you have are greater than 10 capacity, let's say 12, 11, okay, greater than 10, then you can't pick up any item, then your answer should be equal to 0. So if this is the case, then you can simply return 0 as well. Okay, so here you will return a 0. Okay, so 0 plus 1, it's a 10, and here you have again seen a -1, so it is not allowable, so you will return a 0. So now since you are looking for maximum output, you have to compare this thing, you have to take the maximum value, so it will return 10. Okay, so 30 plus 10, it's a 40. So 40 from a right side. Okay, 40 from right side. Now here, okay, so you are currently standing at first index, and you want means you are currently standing at 2 kg wala, and you are looking for 6 kg capacity. Okay, you have 6 kg capacity in your bag. So what you can do, so again 2 is less than 6, so now you will be having 2 choices. One is knapsack of, okay, you can pick up that guy. So if you pick up that guy, your index will move to 0, and your so it's we're currently standing 2, so it will become 4, and you have considered 20 weight, so profit, so 20 plus this one. Okay, and if you decided to not pick up this guy, then what it will become? 0,6. Yes, I hope if you have understood till now, then you can solve problem on your own. Okay, now let me finish this recurrence tree, then we'll go and try to code this up. Okay, now you are currently at a 0th index, means 1, and you are looking for 4 capacity. Okay, and 1 is less than 4, so you can pick up that guy or you can't pick up that guy. So let's say if you decided to pick up that guy, so 10 plus knapsack of, then it will become -1 and a 3. And if you have not decided to not pick up that guy, then it will become knapsack of -1 and 4 itself. Okay, now so -1, it will return 0, so 10 plus 0, it's at 10, it will return 10 here. Now it will return again 0, so 10 is maximum, so 20 plus 10, it's at 30, and again, so you have to solve your left sub or right side sub problem. Okay, so again you are currently standing at 0, and you are looking for the capacity of 6. Okay, so 1 is less than 6, so you can say you can pick up that guy. If you pick up that guy, it will become 10 plus a knapsack of -1 and 5. Okay, if you have decided to not pick up that, then it will become knapsack of -1 and 6. So -1, so it will return 0, again it will return 0, from here 0, then 10 plus 0, it's at 10, and max of this thing is 10, so 30 and 10, so maximum is 30, so it will return 30 here, and maximum of right and left was 40 and 30, so max of 30 and 40 was 40, so your answer was 40. Okay, so is that what we are looking for? Yes. So now let me quickly give a glance, like summary of what I did so far. Okay, so I'm assuming I have a function called a knapsack, okay, where I will be taking my index and a weight and a profits and a weights. Okay, now first we need to write the base cases. What are our base cases? So first thing, if my index becomes less than 0, what I need to do? I need to return 0. Now, or my weight became a 0, my weight became 0. Yes, right, that happens, right? Okay, in that case as well, I should return a 0 only. So this is our base case. Now what is the first condition that we are checking for? So the first condition we are checking for, now the weight which you are currently standing is a greater than weight what we are looking for. If this is the case, so we are standing at let's say we are standing at the weight of 5 kgs, okay, and we are looking for the weight of 2 kgs. Now obviously we can't take that particular item, right? So you should simply return knapsack of index. So you should simply move to next item, and since you haven't picked up that guy, you are not doing any subtraction here, and you will simply pass profits and weights as it is. Okay, so if this is a false, means you can pick up that guy. Okay, you have that choice. Okay, you have that capacity in your bag, so then you will have 2 choices, one to take, another one is to not take. So if you wish to take that guy, what you are doing, so you have to consider that profit of that particular index plus a knapsack of, you have to go to next index. Then you have to, now what you have to do for your capacity, let's say you have a bag of 5 kg and you decided to pick up one guy with the weight of 2 kgs. Now you have to subtract that weight, right, whatever you have taken. So weight of index comma, and so you have to consider profit and weights. Okay, now if you decided to not to pick up that, you don't need to add that profit, you don't need to add that to your profit, then you can simply call knapsack of index minus 1. You have to go to next one and you should not touch your weight. Okay, profit and weights as well as it is. Then at the end you can simply return max of take comma not take. That's it. That's it. Is this what we have done so far? Yes. Yep. So this is what we have done this, and let's simply go and code this particular approach. Okay. And I highly recommend you to try to code this on your own. Okay, so there is nothing special. So till now I have coded this. So okay, stop. Here is the problem statement given. This is interview bit platform. Okay, so please do check out this, and if you wish to submit this problem, please go ahead and submit. So you can simply just search for Knapsack interview bit. Okay. So the problem statement is given something like this. You will be given two integer arrays a and b, okay, of size n, okay, which represents values and weights. So a represents values, b represents weights, okay, associated with n items, okay, and also given an integer c, which represents knapsack capacity, means a weight of the bag, okay. So find out the maximum value subset of a such that sum of weights of this subset is smaller than or equal to C. Okay, so this is what we have discussed, and here you can see the note as well. So you cannot break an item, either pick the complete item or don't pick the, so this is what a 0 1 property. Okay, it's clearly mentioned that. And yeah, let's simply go and try to code this approach. Okay, so okay, let me figure out first a size of the given array, and I'm saying answer equal to knapsack, and I'm passing n minus 1 and a and b and c. So let's go and change these names in the parameter side so that we won't get any confused. Okay, so at the end I am returning my answer. So now let's go and code our main function, like knapsack function. So int knapsack. So first one is index, then it's a vector. So is first one is values. Values means it's a profits, right? Profits. And second one is B stands for our weights. And capacity. This is what we are getting as of now. Okay. So first base condition would be, so if our index became less than 0, so you should not put index double equal to 0. Why? You have to consider the last 0th index as well, right? So it should have some weight and it will have some profit associated with that, so you have to consider that 0th index as well. So don't do this mistake. Okay, so you have to put index less than 0, and your capacity might become double equal to 0 as well. Okay, then you should return 0. No, so done with the base case. Now you have to check the current weight which you are standing at is greater than. Okay, so if that is greater than what you are looking for, then you should simply return, like you should not consider that into your bag. So you will say go to next item, and you should not touch anything. It's and okay. So if this is not the case, what you need to do? Okay, either you can take that. So if you decided to take that, what you need to do? You have to add that particular profit. Okay, so profits of x plus, and you have to go to next element, and you have to do the same task, right? So index minus 1 and a profits and a weights and a capacity. Now here comes the picture. So we have considered that particular we have taken that current element now. You have to minus that particular weight associated with that particular item. So you should do index. Now if you wish not to take up that guy, so you need not to add the profits. You can simply go knapsack, go to a next element and say profit, and say weight, and say capacity. So at the end you should consider a max of a take comma not take. Okay, so this is what it looks like in the hierarchy. In a high level, let's go and test this out. Yeah, so success. So it got success, and if we wish to submit this, what happens? Compiling your code. Yeah, so it failed for some cases where our input is too much. Okay, so means that we need to optimize this particular approach. So basically the constraints here were 10 power 3 and capacity was 10 power 3. Okay, and like so it's a recursive solution, so it will be the time complexity of this particular approach will be exponential. Okay, exponential. So we can't make it through this particular approach, so we should try out something optimizing this approach. So whenever I say optimizing the recursive solution, then one thing you have to remember: dynamic programming. So since we have made a recursive solution, so we can go and convert this particular recursive solutions into the dynamic programming solution using memoization. So for memoization, you need not to do anything. Okay, so you should first figure out what are all the changing factors in your code. Okay, so what are all the changing factors in your code? I can see index is changing and capacity is changing. Yes, capacity is changing. Now you have to keep track of these candidates in your space. Okay, so you have to build a two-dimensional vector, okay, where you can store all these values. Okay, let's say dp of it will be having n rows and how many columns. So here comes the picture, how many columns. So let's say if here if they have given a weight of 50, then you have to check out all the possibilities of weight, which includes a 50 as well, right? So let's say, and your capacity of bag capacity is 50, and you can take the items which are equal to 50, right? Then you have to keep track of that particular index as well. So you have to mention here capital C plus 1 comma, you will be filling with -1 initially. Okay, so now wherever you are making function calls, you have to pass this dp, and whenever you are passing it in your arguments, don't forget to put it in your parameters as well. And int and it's a dp. Cool. So here you are making a function call, and here you are making a function call, and here you are making now. So these are all the 3 steps that we did so far to convert recursive code into memoization. So initially we figure out the what are all changing factors, and then we have created a space for that particular changing factors. Then what I did, so I have added this into my parameters, passing parameters, and I have included that in my function call. So that is second step. Now third step is memoize them. So we are returning your answer here, right? You are returning your answer, which whatever you got till now. So before doing that, just store your answer in the current states, like current indexes. So let's say index and the capacity. So without simply returning that to the user, just store that into your space. Okay, then return. Okay, so here as well. So a dp of index. So you are storing the answer. Now you have to check, okay, before making a function call, you have to just check whether you have already solved that particular problem or not with this current states. So what you need to do, so dp of index of capacity not equal to -1. So if it is equal to -1, it's a new, you have to solve that problem. Okay, if it is not equal to -1, yeah, we have to like it means that you have already solved that particular problem, and you can simply return that as well. So return dp of int capacity. That's it. Okay, so yeah, it's very simple, right? So let's go and test this out. Yeah, it is passing for the sample cases. Now let's submit the solution. Yeah, so correct answer. Yes, I got some 192 points as well. Okay, so please give it a shot. Okay, go ahead and submit this particular code in interview bit. Okay, yes, bye bye, see you in next tutorial. So before moving, just don't forget to subscribe this particular channel, and if you have watched a video so far, please like this video and comment, let me know how you have feel solving this particular problem in the comment section. Bye bye.
Hello everyone, welcome back to Skylar Academy YouTube channel. Myself Vamsi. In this particular tutorial, we will be discussing about another most important interview question on DPs named minimum cost of path sum. So this is the question which has many variations. Okay, so I can say that if you are able to solve this one particular problem, you can go ahead and solve 3 to 4 more problems related to grids on DP. When I say grids, it's equivalent to the matrices. Okay, so I highly recommend you to watch this video till the end. Okay, so before starting, so if you are visiting channel for the first time, don't forget to subscribe. If you like this content, please hit that like button up, and please let us know in the comment section how did you feel about this particular video.
So yeah, now let's discuss about problem statement. So problem statement will be given something like this. You will be given a grid or matrix, or also called as matrix, okay, with the size of m into n or n into m. So you will be given a matrix which is an integer matrix with the size of n into m, and you need to find the, okay, you need to figure out the minimum path, okay, minimum cost, okay, let's say minimum cost that it would take to reach n minus 1 comma n minus 1 from the 0 comma 0. Means you will be starting at the left top corner in the matrix. Okay, so then you need to reach the bottom right corner. Okay, with like inbuilt within the matrix, and you need to return the minimum cost. Okay, minimum cost that would take to reach from that 0 0 cell to n minus 1 n plus n minus 1. So here we will be having few constraints. Okay, so the constraints are from a given cell. Okay, from a starting cell, let's say this is your matrix. Okay, you can only move to 3 steps, like one is to the right, and second one is to the down, and another one is to the diagonally. Okay, so let's say if you are standing here, okay, if you are standing here, either you can move a right, you can move a down, or else you can move a diagonally. Okay, so let's say, let's put some indexes here. So if you are standing at I comma j, then it would be I comma j plus 1, right? Then it would be I plus 1 comma j plus 1. Then it would be I plus 1 comma j. So these are all the steps, okay, that you can do. Then you have to return the minimum cost. Okay, so I will tell you, and I will give an sample input. Okay, let's try our things on that particular matrix. Okay, so you will be given an 3 into 3 matrix. Okay, where input is 2 1 2 3, then a 4 8 2, then 5 1 5 3. Okay, this is the input which you have given. Now you will be starting from this. Okay, you will be starting from this. Now either you can make 3 choices. Either you can move right, you can move this way, you can move this way. Okay, so that's your choice. At the end you have to reach this particular cell, and so to reach that particular cell you will be taking some path, right? So among all the paths which you have taken, you need to return me the one which has took very less time. Okay, very less time. Okay, let's say if you have taken this path, okay, so I have moved diagonally, so I have from 1 to 8, then 8 to 3, then total cost 1 plus 8 plus 3, so it would be like around 12, right? What is another path I can take? So let's say I have moved to 2, then I have moved to 2 to 3, then I have moved to 3 to 2, then again I have moved to 3. So 1 plus 2, okay, 3 plus 3 it's a 6, 6 plus 2 it's a 8, 8 plus 3 it's 11. Okay, another one with the 11. So if I took this path, okay, like 1 plus 4 it's a 5. Okay, 5 plus 1 6, 6 plus 5 it's 11, 11 plus 3 14. So this is another way. And now let's talk about this path. Okay, so if I move to 1 to 2, then 2 to 2, then 2 to 3, like 1 plus 2 it's a 3, 3 plus 2 it's a 5, 5 plus 3 it's a 8. Okay, so this is how you will be calculating. So if you could observe, we will be having multiple paths, so we are interested in only the which is giving the minimum path. Okay, so in this case, for this particular input, this has to be your output. Okay, 8 is the one which gives the minimum path. Okay, so please pause the video for a while here and think of coming up with a solution. Okay, so as of now we have discussed plenty of we have solved plenty of questions on dynamic programming. So first come up with a recurrence relation. Okay, then try out drawing the recurrence tree. Then then we will together convert that particular tree to the code. Okay, so now let's get started. So here, so since we are from the very first video, we are considering only top-down approach, right? Top-down approach means we are starting from the n comma n. This is where we are starting Okay, so then we are reaching the 0 comma 0, right? So here also we will do the same. Okay, if I'm considering starting at this particular cell, then my coordinates will become up, diagonal and left, right? So if I say it's out this one, then it is going to be I minus 1 comma j, then it is going to be I comma j minus 1, then it is going to be something like I minus 1 and j minus 1, right? So these are all the coordinates that we need to identify, like, remember. So let's start. Okay, let's start. Let me quickly have that matrix over here. So 1 2 3 4 8 2 1 5 3. So this is the matrix. Yeah. So now let's start with the recursion tree. So at every index, like at every cell, we do have a 3 choices. Either we can move, if we are starting top and down, either you can move up, can move down, sorry, you can move diagonally, you can move left. Okay, and we need to consider all the paths, and we need to return the one which we are giving very minimum cost. Okay, so let's say we are started at 2 comma 2. Okay, so now what are all the choices I have? So 3 choices. Okay, so first choice is going to be 2 minus 1, then it's going to be 1 comma 1, then it's going to be 1 comma 2. Done. So now let's write the cost of these particular paths as well, so that it will be easy for us to calculate it. Let's say here 3, here it is a 2 comma 1, 2, yeah, 2 comma 1, it's a 5, 1 comma 1 8, 1 comma 2, it's going to be 2. Okay, now from this particular 2 comma 1, again we can make the 3 steps. So one is going to be 2 comma 0, then 1 comma 0, then it is 2 comma, sorry, it is 1 comma 1. Now what is the cost of 2 comma 0? It's a 1. 1 comma 0, it's going to be 4, and 1 comma 1, it's again going to be 8, right? So, and you will go on increase this particular thing again, like you will go ahead and increase on this 2 comma 2, then it is going to be 2 comma minus 1, which is not valid. Okay, so because we don't have any index with the minus 1, right? So so we will return a big number. So since we are considering the one which gives us the very minimum, so we can consider any big number like int max. Okay, now here it is again 1 comma 1, so 1 comma minus 1, so again we are returning int max. So at last it is going to be 1 comma 0, so for 1 comma 0 we will be returning the 4, and we'll go on increase this particular thing again, then we will see something like 0 comma minus 1, so not valid. Again it's 0 comma minus 1, not valid. 1 comma 0 comma 0, valid. So uneven, so whenever you have seen a 0 comma 0, you can't move, like that is the reaching point, right? Whenever you have reached a 0 comma 0, you can simply return your answer over there. Okay, whatever the cost that is, have that. Okay, so here you have 1, so you will simply return 1. So you are done, right? So let's calculate the path from here. So 1 plus 4, it's going to be 5. Okay, so if you carefully observe from here, okay, from here we came to 2 comma 1, so we took this path, okay, and then from here we came to here, and from here we came to here, then from here we came to here. Now what is a path, a cost it took to reach here? So among all these, like intermax, so it will return, so minimum would be 1, and again it is 5. So among all these 3, 5 is the one which is minimum, so you will return 5. So 1 plus 5, it's a 6. So now you need to grow this side, and as you know that for a 1 comma 0 index, so like 1 comma 0, you required a 1, you will be getting 1. So to reach here, you will say you will return 5 here, and we'll go on solve for this guy. Okay, 1 comma 1. Okay, so it is going to be 1 comma 0 and 0 comma 0 and 1 comma 0 comma 1. So 1 comma 0, again you know that 1 comma 0 is going to give you the 5. Okay, 1 comma we will return 5 here, and 0 comma 0. So if you reach 0 0, you will simply return 1, which is the cost that it took, and 0 comma 1, so 0 and 1, so it is 2. Okay, still you have three choices you can make. So you can go 0 comma 0, 0 minus 1 comma 1, so which is not valid, so you will return int max again. So here it is again going to be same story, so minus 1 comma 1, so negative, so you will return int max over here. So the one which is again 1, so it will return 1. So 3, okay, 3, so 3, then you it will return 3 here. Among 5 and 3, 3 is the one which gives the minimum, and 1 comma 1 is 8, so 3 plus 8, it's 11, so you will return 11 here, and from here you will return 5. Okay, and from so here you took path of 1 4 4 plus 5 6 6, you will return 6. So among 6 5 8 11, 6 5 11, so 1 comma 0 will return you 1, so it's a 5 here, 5. So 6 5 11, so you will return 5, and like 5 plus 5, it's a 10. Okay, now you will go this side, and you will do the same task. So I guess it is the one which gives us the minimum. So let's go and draw this tree for this particular thing. Okay, so 1 comma 2, did we solve that problem earlier? No. Okay, let's do this time. So we will be having 3 things. Okay, 1 comma 1, 0 comma 1, and 0 comma 2. Okay, then again it is going to be 1 comma 0, and it is going to be 0 comma 0, and it is going to be 0 comma 1. So you know that 1 comma 0 will return you the 5. 1 comma 0 will return you the 5. So let's return 5, and 0 comma 0 will return you 1, and 0 comma 1 will return you, I hope we have solved this. So here, so at the end, like it is going to return 3. So among all this, 1 is the one which is a very minimum, so you will return 1 here. Now you will go and draw this up, and 0 comma 1, I guess we have solved that, so it will return 3. Okay, so 0 comma 2, did we solve that already? No, I guess. So let's go and solve this up. So again you will be having 3 options. So minus 1 comma 2, which is not valid, minus 1 comma 2, which is not valid, sorry, minus 1 comma 1, which is not valid, and here it is going to be my 0 comma 1. So we have solved, decrease this, we kept this, so we'll keep that, and we'll decrease that. So again 0 comma 1 is going to give you 3, sorry, 0 comma 1 is going to give you 3, and which is very minimum. So you will return 3 plus this 2 comma 05 cost. What is the cost of 2 comma 0 comma 2? 0 comma 2 is 3, so 3 plus 3 is 6, so we will return 3. So out of all these things, so here we will be getting 1, so 1 plus 8 is a 9. So among all these things, so 3 is the one which is minimum. So 3 plus 2 it's a 5, 5 plus 3 is a 8, so here it will return 5. So among all these paths, so you will get 8. Okay, so 5 plus 3 is 8, 3 plus 3 plus 8 is 11, 3 plus 5 is again 8, so the minimum one is 8. So this is how your recursion tree looks like. Yes, it's a messy, but I highly recommend you to draw your own tree. Then only you will be able to solve a few more problems. And this particular problem has a lot of connecting problems. Okay, so here we will be starting from the one particular cell, like starting, and we are reaching the ending. But there will be there will be another problem, okay, where you can start from here, you can start from here, you can start from here. That is valid. Yes, so and this is one problem, and there is another problem. So here we have considered only 3 things, like we can move one diagonal, right, and down. So there will be a problem where you can go 4 sides, left, right, up, down. And there is another problem which tells you go diagonally only, something like this. And there is another problem which tells you to go 8 sides, okay, 4 diagonals, 4 ups and 4 downs, okay, 8 sides. So this problem has lot of connecting problems. So please do solve this one particular problem. Okay, you will get to know 5 to 6 more problems you can solve. Yes, okay, so please Google that. Okay, you will hear a lot about this question. Okay, now let's try to write the code for this particular approach. Okay, recurrence code. So let's assume that we have a function called a get minimum, and we will be getting n comma n. Okay, so where m is our row, n is our column. Okay, and let's write this code. Okay, so what will be our base cases? First base case, can I write if m equal to 0 and n equal to 0, then what we need to return? So we need to return just cost of that matrix, that particular cell. Yes, that is it. And another condition, if either of the either m or n will reaches the index less than 0, then what we need to return? What we have returned in our recurrence tree, we have returned something int max. So let's say 1 e power 9. Okay, 10 power 9. Then in all other cases we need to do something. So what is something? Let's say we do have 3 things, right? Int left. Okay, int left. So if I am moving left, then what it would be? So I am lying in the same row m, and I am decreasing my column. And if I move to up, then get min, I will be decreasing my row, so m minus 1, but I will be residing in same column. And if I am moving onto diagonally, then I am decreasing both my row and column. Now after moving all to the after taking the path in all the options, now what I need to do? I need to choose the one which is very minimum. Yes, so let's say int answer equal to minimum of left comma minimum of up comma diagonal. Yes, then I need to return that answer. This is how, if I write the code, whatever we have seen, this is how it looks like. Agree? Now let's go and code this particular solution. Okay. So at first, what we need to do? We need to have n and m. And then m. After that, we need to take vector of vector. So let's make it as a cost. So where the size would be n into m. And then run the outer loop for m times. And run the inner loop for the n times. Then take this cost of I j. Yes. Now say answer is equal to get min path. Okay, get min path of n minus 1 comma n minus 1. Why n minus 1 comma n minus 1? Because if I took a 3 into 3 matrix, what will be my bottom right corner index? It is going to be 2 comma 2, right? So that's why I have took n minus 1 and n minus 1. So at the end, I will go and print my answer. Now let's go and fill this particular function. So let's say int, then I will be having now what are our base cases? So if whenever n and m equal to 0, then return cost of n and m. You can simply return cost of 0 comma 0 as well. Otherwise, if either m less than 0 or n less than 0, then return 1e9. Yes, if you don't want it to stuck in overflow, then you can simply do -1. And in all other cases, you will be moving three options like left, up, and diagonal. Okay, so if you are moving left, then you will be residing in the same row, then you are decreasing one column and cost as it is. Then if you are moving up, then it's then you are moving column down, row up, then same column, then cost. If you are moving diagonally, then it is going to be get min n minus 1 n minus 1 then your answer is equal to minimum among all these three. So minimum of up comma diagonal. At the end, just return answer. That's it. So let's go and simply provide some inputs. So we are considering 3 comma 3 and we took 1 comma 3. Then 4 4 8 2 1 5 3 4 8 2 4 8 so for this particular input, 8 has to be our output. Let's see. this code and let's build this solution. Took some plenty amount of time, but we got 1 as our output. Okay, sorry. So here we forgot one thing. What is that one thing? Can anyone guess? Basically, if we are taking some path, we forgot to add the cost of that path. Okay, so yeah, it's m plus like cost of sorry, my bad. Yep. Now let's go and save this code and let's run this, build the solution. I think this should give the output. Yes, we got the output as one. Now what next? So the complexity of this approach is going to be big O of 3 into n, like big O of 3 power n into m. Because we have three choices, then it's going to be 3 power exponential. So how can we reduce this? So what is the first step of optimizing a recursive solution to the dynamic programming? So first of all, go and identify what are all the changing factors in your code. So the changing factors, I can see that m and n. So there were two changes every time. So that it means that I need to have a 2D DP. Okay, 2D DP. And int DP of so wherever you are making a call, don't forget to and here let's copy this, let's go up, let's put it here, then let's paste this here and we'll pass in all other cases okay. And at the end so before yeah, let's fill this with -1. Okay, so before making a call, just check whether you have already solved that particular problem or not, then you won't get into an overlapping problems. Then m. So at the last, if instead of returning the answer directly, just store it in your DP and then return. Okay, so yeah, now let's see what it will return. Okay, okay, sorry. So that is right. Okay, so if I give any other input, something like let's say 2, 1, okay, where we will be having 2 rows and yeah, so 2, 3, okay, where we will be having 2 rows and 3 columns. So let's say 1, 2, 3 and 0, 1 and 1. Okay, now I guess our output should be this path. 1 plus 0 it's an 1, 1 plus 1 it's a 2, 2 plus 2 it's a 3. Okay, so yeah, let's run this code up. So yeah, we got 3. So it is returning a good answer. And yeah, so that is pretty much, I guess. And still, if you wanted to do further optimization, I know that I have taught the plenty of times, like how to convert your recursive code to the tabulation method. So please try to do it on yourself. Okay, please let us know in the comment section whether you are able to do that or not.